Okay, we're starting the recording today with AS1020. We're going to do homework 7 on chapter 15. And yes, Shay, the first question does refer to a figure in the book, and I'm happy to share it with you. It's a very important chart in astronomy. It's known as the Hertzsprung-Russell diagram. And you might think of it as sort of like the periodic table of the elements, except for stars. If the most important graph in, hold on, I lost you. If the most important graph in chemistry is the periodic table of the elements, then the most important graph, at least for stellar astronomy, is the Hertzsprung-Russell diagram. It tells you everything you need to know about stars all in one convenient graph. And you guys kind of are introduced to it in a sort of cartoonized form that's easy on the eyes and user-friendly. Let me call it up here because a big part of our day will be spent building up this graph from the ground up. Shoot, I just forgot what number it was. Yeah, it's up here. 1 second. Here we go. This is the chart that they refer to in the book. Now, they're going to ask us in the first question, I'll have you read it in just a moment, Shay. They're going to ask us to compare two different stars. One of them is here. It's the whitish star Sirius. That's the brightest star in our sky. And the other is not the brightest star in the sky, but the closest star to us. It's called Proxima Centauri. And it's actually part of the Alpha Centauri system. It's part of a trinary star system. Not only are there single stars, there are sometimes binaries and even trinary star systems. So I think they chose these two stars just because they're in different locations on the HR diagram, so it will highlight the different properties that we plot on this graph. But also it's cute because Sirius is the brightest star in our sky, and Proxima Centauri is the closest star to us in the sky. Let's take a look at this graph here. This graph is a plot of two things. On the x-axis, don't worry about the letters for now. I want you to notice that we're plotting the surface temperature in Kelvin. But oddly, it's customary to plot the higher temperatures to the left and the cooler temperatures to the right. You can see the cooler stars are more reddish and the hotter stars are more bluish. On the y-axis, we plot their total luminosity. That's the total light output in all directions. We don't measure this in watts in this case, but we measure it in solar luminosity units, or L-suns. That's a solar luminosity unit right there. You'll see me use that a lot today. You'll notice that at 1 solar luminosity unit, the sun is located there, and stars can have a wide range of luminosities, from millions of times that of the sun to hundreds of thousandths of the sun. A couple of other things that need to be pointed out here. It's also possible to measure the radii of stars on this graph. Stellar radii, which are measured in terms of the radius of the sun, increase along these diagonals, and that means that the larger stars are found in this direction, diagonally up and to the right. So Betelgeuse is one of the biggest stars in the sky, whereas Sirius B is one of the smallest. And the very final bit that I'll point out, because this is your first time looking at the HR diagram, is that as long as you're on this diagonal, the red giants don't count here, so ignore the red giants for a moment. Along this diagonal, in this kind of chartreuse color here, or I don't know what color that is, it's light violet or something. Chartreuse is green. What am I talking about? This kind of purpley color plots the masses of the stars from as little as 1/10 of the sun's mass all the way up to almost 100 solar masses. Okay, so now you've gotten a little introduction to the HR diagram. Since you guys mostly don't have the book, I'll just keep this up in the corner as we talk about it. So let's start. Let me erase let me start up the homework here. In fact, this first one we'll conceive it as a table. So Shay, can you read off the question for us?
Yeah, sure. It's a pretty short one, actually.
This
I'm
is
looking
chapter,
at it.
what number is this?
It's 45. Do you want me to list out all the ones?
Yeah, actually I do. Hold on. So we're doing chapter 15, 45. What else?
54, 55, 56, and 57.
Okay. Okay. All right.
Okay.
So chapter 15. Oh, this is sorry guys, I'm still waking up. Homework number 7, right?
Yeah.
Yep.
Chapter 15, by the way, is the sort of general introduction to stars. So chapter 15, number 45.
Okay, it says interpreting the HR diagram. Using the information in figure 1510, the diagram, describe how Proxima Centauri differs from Sirius.
Okay. So why don't we just answer this entire question in a table form? That'll be the most efficient way to do things, and we can compare all the properties at once. So I'm going to have you guys make, I think, 4 columns. The first for the name of the star. The second will be for Sirius. The third will be for Proxima Centauri. And the fourth, we will compare them as we always do with a ratio. And we'll see how many different properties of the star we can get on. So this will be the property. This first star will be Sirius. An abbreviation for Proxima Centauri is ProxCent, and then this column will be the ratio. That's where we compare them. We're thinking at least 6 properties. 1, 2, 3, 4, 5, 6. So you'll see already I have quite a few on my, wow, that looks crooked on the screen, but it's not quite as crooked in real life. That's so strange. Okay. For the properties of stars, the most important properties that we can keep track of for stars are the mass, the luminosity, the radius, and the temperature. I sometimes refer to these things as MLRT. The mass, the luminosity, the radius, and the temperature are the 4 key parameters of a star that help us understand its physics. And it's important because all of these properties can be deduced more or less from the HR diagram. We can also get a couple of other things as well. It also helps us determine the color and even the total estimated lifetime of the star. These are also deducible from the HR diagram. Okay, so let's have you guys play the game. Give you a moment just to finish making your own graphs. Actually, just finish this up while I get some Joe. Assuming that you've all made the graph, everyone's made the graph. Now take a second just to look at the diagram while I zap this. Sorry about that, guys, but this job ain't getting done without the aid of coffee here. I have some water. All right. Tell me what you see. What about the mass of Sirius? What would you estimate in solar mass units? I'll be curious to see how close to the correct answer you get.
In solar radii, like
We will do the radius in solar radii.
oh,
But Evelyn, can we do mass first? Is that okay?
yeah, sorry.
That's okay. The masses are done in a unit. So we're going to compare from now on, rather than work in kilograms and watts and meters, we're going to be working entirely in terms of units of the sun. So Evelyn, your new units are solar mass units for mass, solar luminosities for luminosity, solar radii for the radius. And people don't usually do solar temperatures because there's a relatively narrow range of temperatures. So the temperatures are just going to be measured in good old-fashioned Kelvin. That's the one unit that we still kind of stick to Kelvin instead of comparing it to the sun. So let's start with the mass.
Two on the sun.
Pardon?
Like
Yeah.
2 on the sun.
Yeah, like two solar mass units. This is 1.5 and this is 3. 2's roughly in between. I happen to know, Evelyn, we can see it's just a teensy bit past 2, but not quite 3. Want to go with 2.5 just for fun? I happen to know that I'm pretty darn sure that the mass of Sirius is actually 2.5, so it'll be cute to kind of do it proper like. So we write that 2.5 solar mass units. That's how we do that. It's a circle with a dot in it is the astrological symbol for the sun. Okay, what about Proxima Centauri? We can just use this number, I guess. Can you guys see that?
0.1.
Yeah. The reason why we're going to go with 0.1 is I want to drive home to the class that the lowest possible masses a star can have are 1/10 of the sun's mass. What's the ratio of those two numbers? You don't need a calculator for that. Can anyone do that in their head?
25.
Yeah. Because you're dividing by 1/10, which is the same as multiplying by 10. So it's 25 times. All right. So someone besides Evelyn, since she's played the game, help me get the luminosity here. Which axis gives us the luminosity?
The Y.
Now, this is a logarithmic scale, right?
like
Oh.
10.5.
Oh, no, 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 no. This is 10. Joel, the way a logarithmic graph works is instead of plotting 10, 11, 12, 13, 14, 15, you plot the power on each tick mark. This is 10 to the power 0, 10 to the power 1, which is 10. 10 squared is 100, 10 cubed is 1,000, 10 to the 4 is 10,000.
So it's just 10.
Certainly not. It's greater than 10, but less than 100.
So 50?
Yeah, it kind of looks like it's 50, doesn't it, Shay? Except,
I was just getting confused because I guess like the diagonal lines, that solar radius, I was like grouping them diagonally, but you only do that for the radius, right?
you only do diagonal for the radius. For this, it's perfectly vertical.
Okay.
Perfectly vertical. But, so Shay, at first blush, it would seem like halfway in between 10 and 100 is 50, right?
Yeah.
But the tricks here, and this is kind of maybe one of the learning exercises about this problem, is when you work in a logarithmic graph, the interval between is not quite as simple as it might seem at first. And that's because you're trying to jump from 10 to 100, and it's not going to be even. I wonder, this could be a teachable moment. You know, scientists use logarithmic graphs all the time. And if you're a newbie, if you're uninitiated, they can confuse the crapola out of you. Let's see if we can just find a logarithmic graph. Let's see if we can find one with the tick marks measured out for us so that you guys can get a sense of how this works. Let me type logarithmic scale. Let's see if that, here. Let's see how this does. Okay, this is the kind of thing I wanted to show you something that looked like this. Oh, shucks. Oh, there's a Wikipedia page for it. How cool. Okay, this is what I'm talking about, Shay. On a logarithmic scale, this is actually so perfect for us. Here you can see 10, and here you can see 100, and they're showing you the increments. Instead of it being, you know, we're used to going from 10 to 100 in even increments. Like if you went from 10 to 20, you'd expect to divide the tick marks into maybe 10 boxes or 1 boxes. But here you can notice what's happening is they're jumping by tens. But Shay, can you see how each time they get a little bit closer together? Like the first jump from 10 to 20 is big. The jump from 10 to 30, 20 to 30 is a little smaller. 30 to 40 is smaller than that. You see what I'm saying, Shay?
Yeah, they're like compounding as they go.
Yeah, this is how logarithms work when you're plotting them out, because the idea is you're trying to do that so that it jumps by big numbers each tick mark. So if we're halfway in between, you know what I mean? We're
Yeah.
Like
not
30
quite
and 40.
yeah, maybe 30 is probably our best bet.
That's weird. That's weird
Yeah.
how that's weird.
The first few times you see it, it can really mess you up, and then after a while you just start to accept it and get used to it. So we're gonna go with 30, which I know is a little bit closer to the correct answer. And let's see how we do with the Proxima Centauri.
The government must have set it up.
Huh?
The government must have set it up and did funky math.
Actually,
Conspiracy.
the scientists are the ones who invent this stuff, and then the government usually follows suit after a while with them. F566. All right, so how about prox? I think prox is a little more straightforward. Looks like it's kind of dead nuts at 10 to the minus 3, right?
Yeah.
Okay. Can you guys do that in your heads? Those are solar luminosity units, by the way. Can you divide those in your heads? You should be able to. Who knows how to do that in their head?
Would it be 300?
Not quite, Evelyn. Evelyn, here's how I would do this. Let me go into tile view. Evelyn, let's talk you and me. What is 10 to the power of 3 equivalent to?
Power of 3?
10 to the power of 3? Is not the number 3.
No. 10,000?
No, it's just 10 to the power of 3 is 1 with 3 zeros.
Oh, yeah.
Right?
Yeah.
So revise your answer. What is 10 to the power of 3?
1,000.
Thank you. Okay. So Evelyn, we're dividing 30 by 10 to the minus 3. So what should our ratio be?
3?
I'm sorry? No, you got this. Look.
Just guessing now.
Look, Evelyn, 1 over 10 to the minus 3 is equal to 10 to the 3. And you already know what 10 to the 3 is, right? So if you do 30 divided by this, that's the same as 30 times that, which would be
300,000?
not 300,000, 30
Times 10 to the 3?
is
300,000.
1 0 too many, I think.
Yeah,
You're having
30,000.
30 then?
It's 30,000. It's 30 times 1,000 is 30,000, right?
Oh, yeah, sorry.
It's too early in the morning, Brendan.
I'm just wasting people's time now. I'm just not going to answer.
No, you're not. No.
It's always harder when you're on the spot. Look, anyone can do little things like that. That should not discourage you. You know, if we can't make fun of you, Evelyn, who can we make fun of, right?
Yeah, she's one of the smartest ones in the class, if not me, so we got to make fun of her.
All right, let's try the radius. Let's just check, make sure everyone's here. Okay, let's try that radius now. As Shay, you were pointing out about the diagonals, right? We do radii on diagonals. So Shay, this is also kind of logarithmic-y. We've got 1 solar radius here. We've got 10 solar radii here. And Sirius is about there. Keeping in mind that it's logarithmic, what do you think?
3?
Yeah, that's about what I do, and I think that's the correct answer too. Nice. Okay. So we're gonna go with 3 solar radii. 3 times bigger than the radius of the sun. How about Proxima Centauri?
.1.
Oh, yeah, he's right on the zippity-doo-dah there.
Right on the
Yeah,
zippity. Okay.
Basically right on the line.
All right. So 0.1 solar radii.
Is it just a
Sorry?
I was going to say, is it just a coincidence that it's the same, like the 0.1 of the mass and the radius is also 0.1?
Well, nothing in the physics of stars is exactly coincidence. There is a relationship between mass and radius. Usually more massive stars are a little bigger, but it can be, it's not always so simple. As you will learn today, the 4 properties of stars can be related to each other in a complex way. And if you think about the fact that there are things like white dwarfs and neutron stars and black holes, it is possible to make highly compact and yet massive stars. So it's too simple to say one shoe fits all for stars. But in the case of the diagonal line, which we call the main sequence, today I'm gonna go absolutely bonkers trying to set up this diagonal for you guys. This is what's known in stellar astronomy as the main sequence. And it's extremely important to astronomers because most stars fall on this line when you make a real HR diagram. And this is the line where stars undergo hydrogen fusion. So during the first stage of a star's life, when it fuses hydrogen into helium, like our own sun, they have a very well-defined relationship between mass, temperature, luminosity, and radius. So that's why both of these stars are on the main sequence. And yes, there's a relationship between 0.1, but it's not simple. It's not easy. What's our ratio here?
30.
30 times, okay. Lots of threes happening here.
So Brendan,
Yeah.
if Sirius was an actual black body,
Oh, which it more or less is, right? It is.
well, I mean, if it was, so if it functioned and was quote unquote identical to the sun and how it was a black body, would we wouldn't have a nighttime because it would, is that an accurate assumption?
No, I don't think so.
Because
For the following
it's
reason,
bigger and
it's far away, right? So we'll kick things off in today's lecture by doing a revisitation of the inverse square law, function f(5, 8).
okay.
I don't know what that graph was, but remember, Joel, that a beam of light spreads out as it travels through space and it attenuates or gets weaker. So
Right.
we're detecting it from about 25, I think Sirius is like 25 light, no, I'm sorry. Sirius is 8.6 light years from Earth. So Sirius is a black body, more or less. And it radiates like a black body in every sense. But because it's so far away, the light gets spread out over a huge volume of space, and the actual light that we detect is quite weak.
Okay.
So the inverse square law prevents it from being so bright to block out the night. But
Okay.
but it does function every bit like a black body. In fact, you'll see the spectrum of Sirius. The spectras of stars, as I will develop today, are all quite similar to each other. Now, technically speaking, the spectra of stars are absorption line spectra. But even though absorption line spectra have these prominent absorption lines, you can't forget that they're basically still emitting an almost perfect rainbow of light. So their emission profiles are wicked close to a black body. They're just missing a few lines here and there. So sometimes it's possible to say both are true. The sun emits an absorption spectrum, but an absorption spectrum is so close to a rainbow that it's essentially like a black body.
Okay.
All right, so let's compare their temperatures. Oops, we'll save that for later. Let's compare the temperatures using kelvins. So you can see Proxima Centauri's down here, whereas Sirius is somewhere up here. So what are our numbers going to be?
Sirius is about 10,000 Kelvin.
Good. And Prox?
Prox is 2,800 Kelvin.
That would be a fair estimate, Joel, but I have a secret plan, which is for us to memorize the lowest temperatures of stars is 3,000 Kelvin.
3,000, okay.
So I'm going to be crude only because this is a number I'm going to try to drill into your head, and I'm starting now. The lowest temperatures of stars, roughly speaking, are about 3,000 Kelvin. Plus, with my theme of threes everywhere. We probably could have made that 3 solar masses and 30. That would have been cute. What's our ratio?
3.3.
Yeah. Roughly 3 times. Okay, how about the colors of these bad boys? No tricks, guys.
Sirius is light blue.
Yeah. People. It turns out that A-type stars do have a bluish hue, but my way of thinking about it for now is there are reddish stars, there are some yellowy orange stars, there are some white stars, and there are some blue stars. I actually have a picture. There's a picture of Sirius on its Wikipedia page. And why don't I just show you an actual photograph of the star? It has a binary companion, by the way. Because it's only 8 light years away, it's a well-imaged star. It's the brightest star in the sky, so obviously it gets a lot of play. Here's a beautiful picture of what it looks like through a telescope. And there is a slightly bluish hue to it, but I'd say pound for pound, compared to some stars, like the star, for instance, Rigel, is very blue.
I think cat put me in
Uh-oh, the cat get you?
airplane mode. Oh shoot, I'm not muted. Yeah, I think my cat stepped on the keyboard and put me in.
Cat interference. That's great, Will. I'm glad that your cat's an active participant in this class. So here's a picture of Orion. When I think of a star like Rigel, some stars are really blue. And here's a picture of Rigel, and you can see just how bluish it is. My gut impression from looking at Sirius through a telescope is Sirius is a bit whitish. So it wouldn't have been wrong to say blue, but I'm going to go with white. And then Proxima Centauri is obviously red. We don't need to have a ratio for this. This is just for fun. And the last thing we can get is we can also estimate the total lifespan of these stars. Nuclear physics allows a rough calculation of their total lifespan. We actually did that for homework last time. And this is slide 66. What would you say is the total lifetime of Sirius?
$10 billion.
That's 10 to the 9. 10 to the, that's not 10 billion. That's 1 times 10 to the 9.
Right. So 1 billion. Yeah.
Now, even though Sirius Proxima Centauri is a little bit further down on this line, we're going to use this number as one of the longest lifespans of a star. So we'll use 10 to the 9 years versus 10 to the 11. Hey, Laura, what's 10 to the 11?
Really? I don't know idea.
Let's think it through.
Oh man. Okay.
Wait.
Just add two places to 10 to the 9th.
Right. So 10,
So 100 billion?
yes. 10 to the 11 is
Thanks, Joel.
10 times 10 to the 10, which is 100 times 10 to the 9, right?
Yeah.
That's 100 billion, right? So write it this way. So write 1 billion years for Sirius, but 100 billion years for Prox Centauri. And the ratio, if we keep doing Sirius divided by Proxima, it's 100th, right? So the moral of the story is, one of the reasons why the HR diagram is so important to astronomers is you can just get so much information from it. So much information.
So Prox Centauri will last longer than the sun.
Oh yeah. And the length of time is even longer than the current age of the universe. The current age of the universe is 13.6 billion years old. So there hasn't been enough time in the universe for this star to die out yet, which is crazy to think about. Okay. Has everyone got all this? I can't see a few of you, so hopefully you've had enough time to write all this down. All right. The people I can see seem to be cool, so I'm erasing. All right. The next question is on a new technique for measuring the distances to nearby stars. It's called parallax, and it's probably the easiest damn formula in astronomy. So for chapter 50, oh no, I'm sorry. I take it back, guys. The next problem is going to use the inverse square law. You've already learned this in a previous lecture. The inverse square law tells me that the brightness of my star is the luminosity of a star over 4 pi d squared. So this is the formula we're going to be practicing so we can learn what the brightnesses of stars look like. So Laura, you want to read that for us, number 54?
Sure. 54. Use the inverse square law for light to answer each of the following questions. For part A, suppose a star has the same luminosity as our sun, which is 3.8 times 10 to the 26 watts, but it is located at a distance of 10 light years. What is the apparent brightness?
I'm just going to drive it in as 4 times 10 to the 26 watts, and that was 10 light years.
Yep.
Laura, do you remember what units we measure brightness in?
We measure them in, no, I should know.
You should know. Anyone? Units of brightness?
Oh, is it, wait, no.
Right on the tip of my tongue.
Well, it's an MKS unit. I'll tell you that. What are MKS units of distance?
Kilometers.
Nope.
AU.
Nope.
Light years.
Nope.
Seconds per meter squares or joules per second or something?
Distance?
I don't know. What? Distance? I thought we were talking about light.
Well, you guys can't remember. Here's my logic. You can't remember the units of brightness.
Watts
Maybe-
over meter squared.
That's right. Watts per meter squared.
Yeah, that's what we all said. Yeah.
You just weren't listening.
Now you guys are getting on with my logic.
Yeah, exactly. I see how it is. 4 legs bad, 2 legs good, right? All right. So Laura, we better convert that to meters then, right?
The light years?
Yeah.
Yeah. So
Normally I have you guys go from
light years
to kilometers. But it's also kind of cool to just know the number of meters per light year. It's 9.5 times 10 to the 15 meters per light year.
So that's just 9.5 times 10 to the 16 meters.
Exactly. So let's find it asks us to find the brightness. So we'll do the luminosity of the sun, 4 times 10 to the 26 watts. Over 4 times pi times 9.5 times 10 to the 16 meters squared. I'll let you guys punch the numbers up.
I got 3.5 times 10 to the negative 9
Okay.
watt per meter squared.
That's a pretty dim brightness. You can see, Joel, that if you go 10 light years away, the sun would be just as dim as any other star.
Okay.
Part B.
Part B says, suppose a star has the same apparent brightness as Alpha Centauri, which is 2.7 times 10 to the negative 8 watts per meter squared, but is located at a distance of 200 light years. What is the luminosity?
Let's convert the 200 light years into meters. What's my conversion?
9 times 10 to the 15th on top and 1 on the bottom.
So why don't you guys punch that up for me?
(1.9 times 10 to the 18th meters).
All right. So do you know how to solve for, wait, what are we trying to solve for here? They want to know the luminosity?
Yep, the luminosity.
So I'm just going to take the 4 pi d squared, and I'm going to move the whole thing up here next to the brightness. And the formula becomes L equals 4 pi d squared times the brightness. Four pi 1.9 times 10 to the 18 meters squared times 2.7 times 10 to the minus 8 watts per meter squared.
1.2 times 10 to the 30th.
Units?
Watts.
Right.
Welcome, everyone.
Sweeping into the rescue. What a gallant knight. Here, let me get my calculator too so I can put it on.
Brandon, I have a question too.
Yeah, love to answer.
So this whole graph, like the whole HR diagram, are all of these values just like from our perspective, like closest to our sun? Like if we were looking at all of these stars from like a different location, would all the values be different? Or is it like objectively like that is the size of that star?
It's objectively that is the size of the star. There are things that depend upon distance, and there are things that don't depend upon distance. The brightness depends upon the distance, but the total light output does not, nor does the radius. A pretty decent example would just be a light bulb, right? Let me remember that. I'm just looking for a key picture here while I'm talking. If a light bulb is a 40-watt light bulb, right? That light bulb is 40 watts no matter where it goes. If I plug it in at your house or my house, if the lamp is on the right side of the room or the left side of the room, it's 40 watts. But Evelyn, it does not appear as bright if I'm far away from the bulb as it does if I'm close to it. So if you're sitting underneath your lamp reading a book, then that light bulb is going to be quite bright. But if you're on the other side of the room, it might appear dimmer. So I think what's confusing is there are quantities that don't change, and those are the ones that we're interested in from a physics point of view. MLRT does not change no matter where you go. But the problem is the things that you can observe, the observables, the brightness, that does depend on distance. And you're right to make a point out of it, because the first part of today's lecture is going to be me obsessing with the question, how do I determine the distances to stars? If I can't figure out how far away they are, then I can't figure out any of this stuff. So stay tuned. It's a good point. All right, let's try part C. Oh, box that.
Part C says, suppose a star has a luminosity of 8 times 10 to the 26 watts.
Okay.
And apparent brightness of 3.5 times 10 to the negative 12 watts per meter squared. How far away is it? Give your answer in both kilometers and light years.
Okay. They gave us the luminosity, something times 3.5 times 10 to the 26 watts?
8.
No, 8 times 10 to the 26.
Oh, sorry. Okay. And I'm sorry, I'm just forgetting exactly what you just said.
And the apparent brightness is 3.5 times 10 to the negative 12 watts per meter squared.
Okay. Now, the inverse square law can be rearranged to solve for the distance. And when you rearrange it to solve for distance, that becomes a critical formula in astronomy because of its implications and its applications. It is known to astronomers as the luminosity distance. And the luminosity distance formula is the square root of L over 4 pi b. I'm going to make a big deal about this today. The luminosity distance is the basis for what astronomers refer to as a standard candle. Astronomers love this term, standard candle. If they can find stars whose luminosities are known, they can use them to figure out the distances to stars. In this case, we know the luminosity of the star, and we measure its brightness, and now we'll compute the distance. Everything is already in MKS units, so we don't have to do a thing. The square root, the nice big neat square root of 8 times 10 to the 26 watts over 4 pi 3.5 times 10 to the minus 12 watts per meter squared. Go ahead and punch them up.
$4.2 times 10 to the 18th.
What are my units, Evelyn?
Light years? No, meters.
Meters. Now, they said give the answer in meters, kilometers, and light years. If you ask me, the kilometers are a totally useless addition to this problem because the distance, but I would like to know how far away in light years. So let's start with this in meters, okay? And now let's do a quick conversion. You guys remember that meters to light years is 1 to 9.5 times 10 to the 15. So how many light years is that?
About 450.
Nice. I knew it was going to be far because of that 10 to the minus 12. That's a dim star. Very dim star. Let's box that. I'm going to see if I can't dial me up a sausage, egg, and cheese. I'm feeling hungry today. Wouldn't that be nice if I could get that delivered right to my hand while teaching this class?
That'd be awesome.
I think the girlfriend's going to go to the little market next door, so I'm going to capitalize on her mission. Sorry, guys. Tummy comes first. Okay, let's move on to part D.
All right, so it says, suppose a star has a luminosity of 5 times 10 to the 29 watts and an apparent brightness of 9 times 10 to the 15 watts per meter squared. How
Okay,
far away is it?
guys, I clearly made a mistake here in part D. And this is something you wouldn't notice if I weren't here to point it out, but they've made a very big mistake. Can you tell where the mistake is?
Is it in with B and it being a positive exponent?
Yeah, that's the problem. Why is that a problem, Joel?
Because we would be like,
2 feet away from the star.
yeah, the
Yeah.
distance would be like so stinking close.
Yeah, if you actually punch
And
these
we
numbers
would
in,
get blinded.
yeah, if you punch these numbers in, you get that the star is 200 kilometers away. It's like in Boston or something. So I think they clearly made a typo and they meant to do -15. And that's just because the solar irradiance, the sun's brightness is 1400 watts per meter squared. So if a star is 10
Holy
to the power.
crap.
All right, so they clearly goofed up there. So let's calculate it with negative. the luminosity distance is the big square root of 5 times 10 to the 29 watts over 4 times pi times, oops, I don't need parentheses there, 9 times 10 to the negative 15 watts per meter squared.
Two times 10 to the 21 meters.
Okay, and how many light years is that? I'll just leave the calculation up to you. How many light years is that?
200,000, 210,000.
Okay. That would be outside of our galaxy. Our galaxy is only 100,000 light years across, you may remember. Cool. The reason why you had to practice the inverse square law a whole bunch of times is because it's wicked important for today's lecture. So the more times you use it, the more the concept becomes ingrained in your head. And when you guys are ready, oh, yep.
So how big a telescope would we need to see that? If it's twice our galaxy away.
This is a cool question, believe it or not, that I would like to address. One thing you may not realize when you look at pictures of distant galaxies is that by the time you get to an extragalactic distance, even the Andromeda galaxy, the stars have become so far away that they are no longer resolvable as what I would call a point source, as a dot on the sky. And this is some really important stuff, the kind of cool thing that you want to take away from this class, because you're going to be looking at cool pictures of space in the future and thinking about this class and thinking about the things you've learned. When you look at a picture like Sirius, you can see it as a very bright point source. It's a dot that glows in the sky, but it has an extreme brightness. But you'll notice in the background, I can see a whole bunch of other point sources. And these other point sources must be stars in our own galaxy, because although they might be dim, they're still observable as individual little dots. The trick is that once you get to a distance like Andromeda, the individual stars are now so far away that we are no longer capable of resolving those stars as point sources. Instead, the starlight starts to get kind of smeared out into a uniform paste or fuzz, which you can see here. That also means this. In this picture, which is an interesting picture, any point, single dot that is a star that I can see, must be in the foreground within our own Milky Way. Because I know that there is no telescope on Earth, Joel, that could identify us. Okay, I'm lying to you a little bit. You know, sometimes it's just better to start with lies and then work your way up to the truth. Don't ever take any relationship advice from me, okay? But in anyways, you want to start with lies and you want to work your way up to the truth. And the truth is that there have been a couple of famous results where through hard diligence, Edwin Hubble, and he had to be during a wartime blackout where they were shutting down the lights on the coast of California because they were worried about bombers bombing the major cities. He had such good light pollution control that he famously managed to resolve one star inside the outer disk of Andromeda, and it was a little speck and nothing more. But for the most part, if you can see a star like this star here, that's got to be in the foreground of the Milky Way. Now, this is not a star. That's actually a whole nother galaxy that's in the vicinity of Andromeda. That's a galaxy. So if you see a smudge, that and that are not stars. They're not point sources. They're extended smudges. Those are galaxies. But do you see all these other thousands of little tiny dots? Those are all foreground stars that we are looking through. Another exception to that is there's a couple of galaxies that are outside of the Milky Way that are a little bit closer to us. This requires you to understand something called the local group. And since I think this is interesting and it will help our understanding of the class, I'm willing to burn just 10 seconds on it here. This is a picture, or this is an illustration of our local group of galaxies. So let me give you one of the things I don't get to do in this class is talk about my favorite thing, which is galaxies. And that kind of sucks. So you got to get a little bit of it where you can. Here's the layout. The Milky Way and the Andromeda are big galaxies. They're kind of big, badass galaxies, right? This is like United States and the Soviet Union. But then we're surrounded by some small satellite galaxies that are like, I don't know, the United Kingdom and Canada and, you know, maybe some Yugoslavia, you know, some smaller territory states that are nearby. So the Andromeda and the Milky Way are big, badass galaxies. But we have a number of small, irregular galaxies that surround us. In particular, in our case, I'm thinking about the small and large Magellanic Clouds. They're about 50,000 light years away, and you can actually see individual stars there. So the reason why I was lying to you is if you're looking at these nearby dirtbag galaxies, you can resolve stars just barely. But by the time you get way the F out here to Andromeda, forget about it. So that was a very long-winded answer to your question, but we won't be, when you say how big the question originally came up is, how big a telescope would you need to see a star 200,000 light years away? Okay, Hubble maybe could do it, but the next business of astronomy, as you may not know, is the James Webb Space Telescope. And this thing's already had its launch postponed twice, but it's probably gonna go up in the next year or so. And let me tell you, the James Webb Space Telescope is going to put the Hubble to shame, and it will be the first time a telescope has been capable of resolving stars in other galaxies. Now, just take a look at this bad boy right here in the clean room so that you can appreciate how amazing this thing is. It's an 8-meter telescope covered in gold and beryllium, and it's going to float pretty far away from Earth, so there's absolutely no light pollution. Look at the size of that thing. The whole thing is covered in gold and beryllium. This is got to be like one of the most expensive science instruments ever created. And the bloody...
And it only cost $8 billion.
Well, you know what? So does a nuclear missile. So you ask me, what do you think's a better use of our money? I'd rather have this James Webb Space Telescope, you know?
Yeah.
I think it's, these are preposterous, these are humongous undertakings. But if you think about the fact that before Hubble's Space Telescope existed, you would never have seen a picture like the Pillars of Creation. This high resolution image of giant molecular clouds, which is iconic and mesmerizing and cool, this picture could not have existed before Hubble Space Telescope went up above Earth's atmosphere. And the new telescope is going to be 3 times the diameter. Can you imagine what sort of mind-blowing pictures from space are going to be coming down the pipe in just a few years? It's going to be really, really cool. Stuff like this and crazier than this will be splashed across every newspaper. Oh, hey, Jordan, are you going to Gourmet Heaven? Oh, would you get me a breakfast sandwich? Because I need it. Thank you. Okay. Sorry, just getting the.
So that picture you have on the screen.
Yep.
It's just like gas cloud or whatever, right? That isn't like an actual like something we would see in the desert.
No, this, of course, there are analogies like, no, you may not appreciate just how big this structure is. These are things that I'm building up for us to talk about. Although I'm getting there somewhat slowly. The length of this thing, Joel, is probably like 50 to 100 light years tall. And
Holy crap.
the amount of matter that's inside this thing, if you smushed it down, you could probably make thousands of suns out of it if you crushed it down into stars.
That is crazy.
That is wild.
In fact, it is so big that even though there's thousands and thousands of stars worth of matter in there, it's spread out over such a large volume of space that if you were to like sort of fly through this thing on your Millennium Falcon, okay, like let's say you had a spaceship and you took your flying saucer on a journey through this thing, you would be so small in comparison to this that the gas would still be almost like a vacuum compared to the amount of air you're used to breathing. In fact, it could be that our own sun and solar system is buried inside of one of these things, and we wouldn't be that aware of it because the gas density is still thin enough to look out of it. So trying to figure out whether you're inside one of these things is actually quite a difficult piece of business. You only notice it being dark and clumpy like if you observe it from crap loads of light years away. So it's very interesting. These things can block light, but they allow some light through. So it can be difficult to even figure out if you're inside one. So those are what are called giant molecular clouds, and that's where star formation takes place. That'll be a part of our lectures next.
Or maybe we are.
Say that?
I was going to say, maybe we are inside of that cloud and we're looking at ourselves.
It's a
right
very
now.
strong. Wait, is this some kind of metaphor for our confusion in the class? I didn't know how deep you were going with that one, Will.
That was pretty deep.
Brendan, as long as like we've been monitoring, or when the pillars of creation were discovered, or that we could see them, does it morph much? Does it like really keep its structure?
If we lived longer, if we could live for hundreds of millions of years, you'd probably see it morph over time. But the problem is those things evolve over time scales. It's kind of like a mountain growing, right? Mount Everest increases its height by 1 centimeter a year or something. I don't actually know what the rate is, but I bet it's slow like that. But in 100 years, you don't notice Mount Everest grow much. But if you were around for a long time, you guys know what some of the oldest organisms are on Earth? The bristlecone pine, I think 5,000 years old. They live for 5,000 years. But you'd have to live even longer than that to notice the cloud morph. You'd have to live for hundreds of thousands of years. But they are changing. Okay, in our next problem, in problem 55, we are going to use one of the easiest formulas in astronomy to measure the distances to stars. It's called the parallax formula. And parallax is an angular shift in the displacement of stars. I'll explain it all in good time. The formula is pretty simple. The distance to our star is just 1 over the parallax shift. Here, I'm using the Greek letter rho to represent the parallax shift. It's an angle, okay? It's an angle measured in arc seconds. So it's going to sound weird to you at first. We measure an angle in arc seconds and we get a distance. D is the distance in a new unit called parsecs. A parsec is 3.26 light years. That's your conversion. Now, I need to explain this formula to you, but it's very, very easy to use. Just take the reciprocal. So Shay or anyone, why don't you read out the 55 for me?
Okie doke, 55. 55, parallax and distance. Use the parallax formula to calculate the distance to each of the following stars. Give your answers in both parsecs and light years. A, Alpha Centauri, with a parallax angle of 0.7420 degrees.
Wow. Okay, let's try, not degrees. It can't be degrees. It's got to be.
Oh, yeah. Yeah, I can't see the, yeah, I can't make it. Yeah, your arc seconds, yeah.
All right. They've given us 4 sig figs there, right? So I guess we can roll with that. It's a little overkill, but. So I don't know how to explain this, but it's just that simple. The only way I can teach you something useful here is to teach you a new key on your calculator called the reciprocal key. I'm going to ask you guys to punch it in a funny way because this key could come in handy at a later time in our course, although there's not that much time left. I want you to start by just typing in the number 0.7420. And I'm going to ask you to do this in a funny way, just for kicks and giggles. Above your closed parenthesis key is a key in orange called the reciprocal key. It's 1 over x. So just hit Shift, close parentheses. That's just a cute way of flipping a reciprocal. If Evelyn is still using her TI-85, it's an x to the -1 key. What's our answer?
1.35.
We could keep 4 sig figs if we wanted to get crazy.
1.347 or 8.
Honestly, it's overkill. It's too much. And that's parsecs. Let's convert parsecs to light years. Actually, my memorization of the of the conversion factor from parsecs to light years is only 3 sig figs. So this is one of those weird cases where our conversion factor is going to pollute our answer. 1 parsec, 3.26 light years. So give me the distance in 3 sig figs.
4.39.
Light years. All right, part B.
1 sec. Okay, part B.
Do you need time to finish writing that, Shay?
Actually, I'm all set.
Okay.
Just gonna box it up to make it look classy.
Yep. Always.
Okay, B is procyon or procyon?
Procyon.
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 Procyon with a parallax angle of 0.2860 arc seconds.
Okay. So the formula is wicked easy. Just distance is 1 over 0.2860 arc seconds.
$3.497.
parsecs. And then we'll go from parsecs to light years. 3.26 light years per parsec.
11.4. Like,
Nothing to it. That's one of the best formulas in all of astronomy. It's real easy. Okay. Oh, wow. I really talked a lot this office hours. I didn't realize how behind the gun we were. I'm so sorry about that.
We all have.
Wow. All right, let's move on to 56. I did not realize how slow I was going. All right, 56 is a real weird concept with a formula that's going to look funny to you guys, but it's not overly complicated. It's about the magnitude system. The magnitude system is a way of ranking the brightnesses of stars. It's going to take a little bit of getting used to, but the concept starts off simple, and then it starts to actually get more confusing over time. And let me just explain the basic idea. It's part of today's lecture. The magnitude system is a ranking of stellar brightnesses. 34. And what's goofy about it, it was invented thousands of years ago by the Greek astronomer Hipparchus, and weirdo astronomers continue to use it today. So the idea was the brightest, oops, that's not what I wanted, that's a stamp. The brightest stars that Hipparchus could see, like Betelgeuse and Sirius and stuff, he called them a rank 1 star. And the second brightest stars, which would be like in Orion's belt, he would call a rank 2 star. And he ranked all the stars he could find into 6 classes, rank 1 through 6. But what's weird about the system that he kind of intuitively chose is he wasn't thinking mathematically at the time. So he awkwardly made the smaller numbers the brighter stars, and he made the bigger numbers the dimmer stars. Because we've used this for so many hundreds of years, we've now extended this beyond these values. The actual magnitude of Sirius is now -1. The magnitude of the sun is -27, so it's kind of a mess. But there's a relationship, a very tricky mathematical relationship between magnitude and brightness. So let's say I've got 2 stars. I'm going to call the bright star the A star, and I'm going to call the dim star the B star, just to say star A and star B. And the ratio of brightnesses, if I wanted to divide the A star brightness by the B star brightness in watts per meter squared, is the number 100 raised to the power of the change in magnitude divided by 5. That is 100 raised to the power of MB minus MA divided by 5. I've used the caret to signify raised to the power of, so that our notation will be clear. Okay, that's not enough description for you guys, but who cares? Let's just read the damn thing off and see what we can do.
Okay. The magnitude system. Use the definitions of the magnitude system to answer each of the following questions. A, which is brighter in our sky? A star with apparent magnitude 2 or a star with apparent magnitude 7?
Okay. The magnitude 2 star is going to be brighter than the magnitude 7 star because smaller magnitudes are brighter stars. We're going to calculate first the difference. Let's calculate the change in magnitudes. 7 minus 2 is 5. So the ratio of star A, well, okay, let's put in the magnitude. The ratio of a star with a magnitude of 2 to the ratio of a star with a magnitude of 7 is 100 raised to the power of 5 divided by 5. Y'all know what the answer to that is?
100.
Yeah, that's 100 to the power of 1, or 100. So we say a magnitude 2 star is 100 times brighter than a magnitude 7 star. Okay, what's the next one?
B is which has a greater luminosity? A star with absolute magnitude -4 or a star with absolute magnitude +6? And by how much?
Okay, the formula for luminosity is the same as the formula for brightness. The luminosity of star A divided by the luminosity of star B is the difference in what we call their absolute magnitude. Absolute magnitudes and apparent magnitudes are basically the same thing. So what we're going to do is we're going to say the luminosity of the -4 star compared to the luminosity of the +6 star. Well, first of all, what's the change in magnitudes here?
And
10?
10. Yeah. 6 minus 4. 10. So we have 100 raised to the power of 10 divided by 5. What's 100 squared?
10,000?
Yeah. So an absolute magnitude -4 star is 10,000 times more luminous than an absolute magnitude +6. The magnitude thing I got to explain better, and I will do that.
Yeah, it's just that it's like reversed.
Yep, that's one of the issues. Not only is it reversed, Shay, but remember how I showed you that weird logarithmic scale?
Yeah, right. It's the
It's
same.
reversed and it's logarithmic.
Yeah. Yeah, it takes a little time to wrap your head around.
It sure is. Magnitudes are very confusing. That's why I'm not even trying to explain it all right now. I'm going to wait till lecture.
Yes, there's no way I would be able to understand it right now, I don't think.
Oh, no, you will. We just have to take it slow. Okay, so just get all that down and put it on ice. We got one more problem to do. I'm going to see if we can beast it out pretty quick here. Actually, so our last, I got a different idea. Our final problem is a problem on calculating the masses of binary stars. That also happens to be our lab today. So the first part of today's lecture, I'll be lecturing on all the stuff we just did. And the second part of today's lecture, I'll be talking about binary stars. Why don't we give ourselves a break, go easy, and we'll do the final homework problem a little later on when we're ready to shift gears and talk about binary stars. Everyone cool with that? You like taking a little 10-minute break or so, 15-minute break until we start lecturing? Freshen up? Okay. Jose, you down with that? Okay, cool. All right, everyone seems to like it. So let's give ourselves a little pause, take 10, 15 minutes, and then we'll come back, okay?
Okay.
All right. Hi, everyone. I guess I never paused the recording, so that's going to stink for anyone who watches this later. Shay, now I not only need you to remind me to record it, I also need you to remind me to pause the recording.
To unrecord. You know, I thought about it. I thought about doing that, and I was like, no, he'll do it.
Yeah. No, I could smell breakfast sandwich, so I went feral. Hey, what's our last note on the sun? I know we kind of did the interior of the sun, but I don't think we did the nuclear fusion stuff right. I remember it as being the inner layers of the sun.
Yeah.
I got one module to do then before we get into chapter 15 on stars, and that's nuclear fusion in the sun. Pretty sure we didn't do this. Let's take some notes. Hydrogen fusion is a reaction that generates energy inside the sun. And the particular reaction that we're here to discuss is known as the proton-proton chain. Sometimes unimaginatively called the PP chain, okay? Now, before we get into a discussion of the proton-proton chain and fusion, I thought I would take a second to ask y'all if you know the difference between fusion and fission, and if you know anything about nuclear reactions at all, because for many people, this is their first foray into nuclear science, so we might want to take this one by the numbers, you know? So, fusion versus fission. Tell me what you know. What's the difference between, let me ask a simpler question. What's the difference between a nuclear reaction and a chemical reaction? Not sure?
Something with like the number of atoms involved.
Not so much the number of atoms.
Temperature?
Well, nuclear reactions do occur at higher temperatures. So temperature is relevant, but it's not the deciding factor. Last week, I went through great pains to explain to you guys that the sun is not a ball of fire. And I shared what I think is a pretty important slide, slide 24, in explaining what a chemical reaction is. A chemical reaction is when molecules swap their dance partners. When molecules break apart and the atoms jump ship from one molecule to another molecule. So this, for instance, is diatomic oxygen. These are two oxygen atoms that are lumped together. And if I mix 2 parts oxygen with 1 part methane, that's 1 carbon and 4 hydrogens, I get a very violent chemical reaction which produces light. But what's happening is the hydrogens are getting ripped off of the carbon by the oxygen. Oxygen would rather be part of a water molecule than it would be part of a diatomic oxygen molecule. So the oxygen rips the hydrogens off and it creates water, and then carbon dioxide forms as a byproduct. But the reason why this is chemistry and not nuclear physics is because the atoms themselves did not change. So the oxygen atoms on the left still stay oxygen on the right. The hydrogens on the left will still remain as hydrogen on the right. and the carbon will still be carbon when it gets to the other side. Now, the molecules are not the same, but the atoms themselves are. Let's contrast this with a nuclear reaction. Nuclear reactions are crazier because you're actually changing the nuclei of the atom, and therefore you're changing the atoms themselves. And I've got a slide that might help us here. This is a little digression between the difference between fission and fusion. So in both fission and fusion are types of nuclear reactions where the nucleus of the atom itself gets morphed or modified. A fissure is a crack. And when you do fission, you crack apart a big fat nucleus like uranium-235. One way to crack apart a nucleus is to shoot a high-speed neutron at it, kind of like if you were playing a game of pool. The cue ball is going to break apart the triangle there. And uranium-235, which is already kind of on the edge of being unstable, will split apart into what are known as daughter nuclei. They themselves are radioactive cesium and rubidium. It also releases a lot of energy, usually in the form of really short wavelength light called gamma rays, and it even spits out a few extra neutrons that will go cracking into other nuclei. But the idea behind fission is you break a big nucleus into littler nuclei. Fusion is the opposite of that. It's still nuclear physics, but here you take small nuclei, like these deuterium nuclei or deuterons, and you smack the deuterons together, which deuterons are still hydrogen, they're just hydrogen 2, and you smack the hydrogens together to form helium 4, which is a different atom. It's helium. Weirdly, putting small nuclei together into bigger nuclei will also release energy, just not as much. So fission is very violent. Fusion is a little bit more gentle. The sun uses fusion as its power source. Us humans, we've more or less mastered using, not mastered, but we are capable of performing fission reactions. We haven't really figured out how to do fusion as well as the sun does. Fusion's been a difficult job for us, although it would be very beneficial for reasons of environmental science. What else should I say about this? Oh, just as a little additional bonus to try to make the day fun, I think I've got some cute little physics Java apps on fission and fusion, and maybe we could poke around with those just for a second, just to have a good time. I've got two. One is on something called beta decay. That's how a nucleus will spontaneously pop. And I also have one on nuclear fission. Let's start with this one. So I know you guys probably love The Simpsons, right? What's Homer Simpson's job at the nuclear power plant? What does he do? Do you remember?
To blow it up.
No, his job is to not blow it up. Right?
But he's always blowing the place up. So then his job?
All right, so his job is a nuclear control rod technician, if I remember correctly. Let me share the screen with you guys. Here's an example of fission. This is a big fat uranium-235 nucleus. It's already unstable. It's on, it's on the edge of stability. And what I'm going to do is I'm just going to shoot a high-speed neutron into it, and let's watch what happens. Whoop, boom. It splits apart into daughter nuclei, and it emits some energy in the form of gamma rays, and a couple of extra neutrons go flying out. Let's see if we can make a chain reaction here. I'm going to populate this field with a whole bunch of uranium-235s. And I'm going to fire a single neutron to get the game going here and blow this one apart. And we'll see if any of the neutrons that it shoots out is capable of stimulating these nuclei. Poof, 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 poof. Whoa. Now, actual uranium usually contains a mixture of U-235 and U-238. So let's make a mixture of U-235 is much more unstable than U-238. Let's do half and half and see what happens. Oof. Ooh. Sorry, I hit the U2. Is that U? Yeah, I hit the U-238. So it didn't really do much of anything. Did this doodad crash or what? Okay. You guys want to see a runaway nuclear reaction? This is when it goes crazy. Let's just fire this into a bunch of U-235. Huh. Poof. Poof, 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 poof. That's bad business right there, right? Now, in a nuclear power plant, when you undergo nuclear fission, Homer Simpson's job is to adjust the depth of the nuclear control rods, okay? Now, the idea is that you have all these rods filled with uranium-235 and uranium-238 as a mixture. Usually you try to purify it so it's just uranium-235 because that's the unstable one that produces energy or that breaks apart more easily. And we're going to fire some neutrons in. Now, if I bring the rods all the way up and I fire the neutrons, they generate a little bit of energy, but the reaction tends to peter out, and then you don't get anything out. On the other hand, if I bring the rods all the way down and I fire the neutrons, now you're in big trouble because usually this will happen. You'll have a meltdown like Fukushima or Chernobyl where all the neutrons shooting out just create a runaway. This is a runaway chain reaction. Actually, that one proceeded relatively mild in terms of energy, but what you want to do is you want to adjust the rods and fire the neutrons, and then the game, hold on, let me reset this again. I want to keep your faces over here. You want to adjust the rods so that you maintain a steady power output, but you don't have a runaway reaction. So you keep making adjustments to slow the rate of the reactions and then to get them kicked off again. Once the nuclear rods have been spent, they become basically toxic waste, right? They become nuclear toxic waste. Do you guys know what we do with these spent nuclear rods once they're done?
Bury 'em.
Yeah, we bury them in Yucca Mountain, New Mexico. New Mexico has a town called Yucca Flats. Probably not the greatest place to buy property. And they have a mountain there called Yucca Mountain. And they bury the spent nuclear rods. Inside Yucca Mountain, they have a giant cavity, which is first lined with lead and then with concrete. And they throw the leftover cesium and rubidium rods in there where they will continue to be radioactive for millions of years to come. Yes, Evelyn, that does sound horrible, but guess what? Things aren't always what they seem. Most environmental scientists are pro-nuclear reactions or pro-nuclear reactors as a means of generating electricity. Because yes, Evelyn, it is terrible to create a nuclear sludge and dump it into a cavity in the mountain. But consider the alternative. Burning coal and fossil fuels puts carbon into the sky, which will overheat the planet and kill every bloody organism on Earth, including all the cute little puppies and squirrels. So while carbon might seem less harmful because it's not nuclear sludge, the nuclear sludge can be contained. The carbon cannot be contained, and it overheats and kills everyone. And the only third alternative is for everyone to switch off their Nintendos and their iPads, and that ain't never gonna happen, right? So because we're addicted to juice, because we need this electricity, you've got two options to make it. You burn coal and pump fossil fuels into the sky, which overheats the planet, or you run these nuclear reactors and you try to keep it under control, keep it from having a meltdown, and you put this small amount of highly toxic waste in one mountain until we can figure out a better solution. Wouldn't it be cool if we could make nuclear reactions the way the sun did? Because if we could harness fusion instead of fission, we wouldn't have these dirty, nasty byproducts. The sun's version of nuclear energy is clean because it builds up small nuclei into bigger nuclei, and it doesn't create these leftover radioactive daughter isotopes that are the toxic waste or the toxic sludge. The problem with fusion is that fusion requires stupidly, stupidly high temperatures. And we have not figured out how to take plasma and get it as hot as the interior of the sun can. The reason why the sun can perform fusion is the sun is a massive sphere of 2 × 10⁻�30 kilograms. And it's just crushing its gargantuan mass down on the center of the star until it gets high enough for fusion. For us, the problem with trying to bring the temperature of a fusion reactor up to the 15 million Kelvin it requires is you very much do not want your control room where the scientists are to be at 15 million Kelvin. That would be unpleasant working conditions. So our initial stabs at trying to create fusion were these devices invented by the Russians in the 1980s called tokamaks. A tokamak reactor was basically a giant metal donut that was a huge solenoid. I want to show you a picture of them because they look kind of cool. This is the picture of an interior of a tokamak reactor. It's basically a humongous cylindrical donut made of metal, and the whole thing is wired with very powerful wires which create a super potent magnetic field. See, it's not like a thermos. You can't have plasma at 15 million Kelvin and keep it in a bottle because the edge of the bottle will get too hot. So what you do is you create these magnetic fields and you try to trap the plasma. Here, let me show you a cartoon of how it works. You trap the plasma inside the magnetic fields, and by spinning the plasma around and heating it up, you can have this donut of plasma that doesn't ever touch the walls of the container. It's a great idea, but the problem is it doesn't work. They had these things going and they had to keep dumping more and more energy into the magnetic field to trap the plasma that they couldn't get to the break-even point. And I think at some point, the reactions got so difficult that at Princeton, New Jersey, the lights in the city were dimming because they were draining the town of so much energy. And eventually the congressmen were like, we're not funding this shit anymore because you guys aren't actually getting anywhere. And people were frustrated. Today, there is new research being done into fusion. And I should mention this because it could become an issue politically, or it could become an issue for humanity that we should know about. The deal with the newest types of nuclear fusion is the NOVA project in France. They take a deuterium pellet and they simultaneously shoot it with like 20 lasers at once and try to superheat it into a fusion reaction. And apparently, I've read that the NOVA project actually hit the break-even point a few years ago, which is considered a technical milestone on the road to fusion. If you guys can understand the implications of this, if we could achieve nuclear fusion, we would have free electricity for life, and it would be 100% environmentally clean. It would satisfy everyone, and then it would be free juice and good for the planet. But it's very difficult. So this is the NOVA fusion project. I wonder if I could find a
but there's one problem with that.
What's that?
That F word you said.
A fusion?
No.
Free?
Free.
Oh yeah. Well,
the government can't make money off us if it's free.
Right. Well, the
government.
Okay, so it will be a cheaper. All right, it'll never be free, but it will be a cheaper form of electricity than we have today. It'll solve the crisis because it'll be both cheaper and it will be environmentally friendly. Our problem that we have now is the cheaper the source of electricity, the more totally evil it is for the planet. Like coal. Well, actually, coal's not even cheapest anymore, so that's good. But it still costs a little too much money to put solar panels everywhere. You don't. It's a long-term investment. Anyways, now that I've given you that preamble to try to help you understand why it's important in our lives, maybe I'll show you guys my rock of uranium. I actually have a rock of uranium. Maybe you'd like to see that. Let's first learn about the details of the proton-proton chain while I've got your attention. It's going to proceed in 3 steps. And the steps are kind of laid out nicely in this picture here. I think I like the picture that I showed you earlier, which kind of shows the whole thing laid out. There's two branches of the proton-proton chain. And I'm just trying to get this tucked out of the way here. This is the first stage here. This is the second stage, and this is the third stage. But why don't we start with the overall reaction? And I'm going to kind of use some technical symbolism here. Introducing the proton-proton chain. Now, the overall reaction, which I like to start with, is that 4 hydrogens are going to collide, and they are going to fuse into 1 helium atom and 2 gamma rays. All right? And I think we might want to draw this out symbolically so that you can appreciate it. A naked hydrogen atom is just a proton. So basically we're taking 4 protons, 1, 2, 3, 4, and we're going to smush them together to make 1 helium. That's 2 protons and 2 neutrons. And we're going to make 2 gamma rays. I like to purple for gamma rays because it's on the blue end of the electromagnetic spectrum. Remember that gamma rays are a form of light, and they're one of the 3 types of radiation discovered by Madame Curie. All right, so 4 hydrogens are going to come together. Now, I don't know if you guys can see what the problem with this is here, but 2 of our protons are going to have to magically transform themselves into neutrons. And the way they're going to do that is by creating antimatter. Okay, so here's where things are going to get a little nutty. Let's take a look at the deets on the reaction. I'm racing. So these are the 3 steps of the proton-proton chain. In step 1, a proton, which is a hydrogen atom, slams into another hydrogen atom, and it forms something called a deuteron. Usually the symbol for a deuteron is a D with a plus next to it. What's a deuteron, you say? Well, why don't we draw the picture out symbolically? The hydrogens are just naked protons. And one of the protons is going to transform itself into a neutron. When it does so, the neutron and the proton will bind together to form the nucleus of deuterium. And the nucleus of deuterium is sometimes referred to as a deuteron because there's 2 particles there. Why this is possible is because a neutron is actually a particle which is created by smushing together a proton and an electron. So you can actually take a proton and you can take an electron and you can smush them together to create a neutron. The one weird problem with this arrangement is that we realized that protons and electrons were sometimes smushing together to create neutrons when we began experiments with particle colliders. But when the physicists measured the masses and the energies of the proton and the electron, and they compared it to the mass of the neutron, they discovered that the mass of the neutron was just a slightly teensy-weensy tiny bit bigger. And that caused the scientists a great amount of concern because they thought, well, whatever stuff is on this side of the equation has to equal the stuff on that side of the equation. And the proposal was that perhaps there was something missing. And Enrico Fermi, the scientist who proposed its existence, called it a neutrino, which means little tiny one. And he hypothesized that there would be this little tiny magical particle with no charge, and this little tiny particle would make up the slight difference in mass. It took us decades. At first, people didn't even believe him. They thought it was crazy talk. It took decades and decades for people to discover these neutrinos, but we eventually learned how to detect them. And now there's a big branch of physics and astronomy that deals with neutrino science. What makes neutrinos cool is a neutrino has no charge, not positive, so it's kind of like a neutron in that sense. But it's so microscopic and so tiny that most atoms just appear like empty space to a neutrino. So a hydrogen atom to a neutrino looks like a microscopic proton and a very distant electron. But the neutrinos can fly right through the atoms with an almost 0% chance of striking either the nucleus or the electron. In fact, so tiny and so microscopic are neutrinos that the sun to a neutrino is basically like transparent glass. The sun produces neutrinos every second, and they are capable of flying through the radius of the sun without even striking a single atom of hydrogen. In fact, they're also capable of traveling through the Earth without striking a single atom. During the course of today's lecture, neutrinos from the sun will pass through the sun's radius, take an 8-minute journey to your house. They will fly through the cells and atoms in your body and fly through Earth and continue on their way through intergalactic space. I think the rule of thumb is that in order to have a 100% chance of stopping a neutrino, a 100% chance, you need to pass a neutrino through a slab of lead that is 1 light year in thickness. So if you pass a neutrino through a 1 light year slab of lead, it will bump into 1 lead atom. But guess what? If it's only half a light year thick, there's a 50% chance it'll get right through without hitting anything. That's how stupid these things are. Now, because of their stupidity, when Enrico Fermi and friends first proposed this, people said, okay, wait a minute. You're telling me that there's a particle that I've never seen, and it exists, and I can never detect it. And he said, pretty much, yeah, that's right. There's this particle, you've never seen it, and you're never going to be able to detect it, but I think it's there. And people were like, dude, what are you smoking? That's not how science works. You can't just make shit up. And for years, people would occasionally take stabs at trying to detect these neutrinos, and they would inevitably fail because the neutrinos, if they were there, would pass right through your damn detector. And then some clever bastards discovered that there was a molecule in commercial dry cleaning fluid that had a higher probability than average of getting struck by a neutrino. And they went and they invented the world's first neutrino telescope in a mine shaft in South Dakota. 2 miles down, they built the Homestake Solar Neutrino Observatory, and it was a 400,000 liter vat of cleaning fluid that they put inside of a giant tank 2 miles underground, and they coated the tank with really sensitive gamma ray detectors, and they sat there in the dark and waited for neutrinos to bump into Mr. Clean and create tiny little sparks. And sure enough, the neutrinos struck the Mr. Clean, and they began detecting them from the sun. So this is the world's first neutrino telescope. It was called a 400, it's just totally nuts.
I have a question.
Now, oh yeah.
Does this have anything to do with dark matter as well? Do they use that for For dark
So,
matter?
it's a
that totally
related
different?
problem. So today in the neutrino thing has kind of, I won't say it's been solved, but we learned so much about physics by studying neutrinos that it emboldened us, Will, to attempt other versions of this same experiment. So one of the big problems that we have in physics, cosmology, and astronomy right now, they're all part of the same science, is that there's 5 or 6 different lines of evidence that are pointing to the fact that there is a ton of mass that is not accounted for in our galaxy that we somehow cannot see because it's not giving off any light. All the calculations based on the rotations of the galaxies and the speeds of the stars, they're all pointing to the fact that there's some. You can also prove that the mass isn't some central object like a black hole, but it's got to be a smeared out paste of something. They actually considered neutrinos as one of the possibilities for dark matter because although they're very tiny, they have a small amount of mass. So given a galaxy-wide field of them, maybe that could do it. But it turns out that no matter how hard they tried, they cannot come up with enough neutrinos to account for dark matter. So today neutrinos have been ruled out. But what they're doing is they're doing similar experiments like this because they had success with this. Today, there's a cottage industry of physicists, including some up at Brown. They do a lot of dark matter detection at Brown. And I go to their talks sometimes, and oh my God, these poor sots. They have these giant detectors full of exotic gases like xenon and elaborate metals. And they sit there just waiting for a dark matter particle to bump into one of their things. They're trying to find the next Mr. Clean, right? And then you go to the talk and they have like 20 data points and they'll be like, well, we've got to rule out this data point and this data point and this data point. And after you get to the 1 hour lecture, they have 1 data point left and they say, and that might be the dark matter, you know? And by that time, you're just like, get the hell out of here. But people said the same thing to these guys. And then one day they started detecting them and it was a big deal. Let me tell you why it was a big deal. Based on our calculation of the rate at which the sun produces nuclear fusion, we expected to get something like, I don't know what it was. It was it was something like 16 neutrinos per day or something from the sun. And they found exactly 1/3 the number of neutrinos that they were supposed to detect. This for years when I was a student was known as the solar neutrino problem. It was you expect to get something like 12 neutrinos per day, but instead you get 4 neutrinos per day, and it was exactly 1/3 the predicted amount. And it drove people mad because they said, our calculations seem so good, but we're getting exactly 1/3 the number we predicted. Why is this? And the answer turned out to be so freaking nutty. To explain it to you, I need to show you the standard model of physics. It's really hard to explain your first time around just how weird physics has gotten in the modern sense. So they discovered that the reason why there were exactly 1/3 the number of neutrinos detected from the sun is because there turned out to be 3 flavors of neutrino. Okay, wait for this. There is not one neutrino, there is an electron neutrino, a muon neutrino, and a tau neutrino. And the reason why they were only detecting 1/3 is because as a neutrino flies through space, it oscillates and morphs between the 3 flavors, oscillating from electron to muon to tau, but they could only detect the electron neutrinos at their detector, so they were always getting exactly 1/3. It was just so insane. So, Will, that's deeply related to your question because think about how the study of neutrinos broke open this whole weird world of physics that they hadn't seen before. People are hoping that if they can detect these dark matter particles, it's going to open up this whole new dimension of physics and our knowledge of reality that's going to be profound and cool. So there's a lot of people doing this kind of a thing again to see if they can kind of get the next neutrino, if you will, right?
But
I'll
if
say
we
this
can't, if they're so small, we can't see them. How do we measure them and know that there's 3 different levels or
That's a fair.
stages of?
So the answer is through collision. So you can't directly observe the neutrino, but what happens is there's a molecule inside of Mr. Clean where some arrangement of the neutrons means the neutrino is more likely than average to hit it. When the neutrino hits it, it creates a little tiny nuclear reaction that emits a gamma ray. And then you line the walls of your tank with photosensors that detect the gamma rays. And you argue every gamma ray I detect was caused by a neutrino. In fact, because they had luck with Mr. Clean, they also realized that deuterium, would have a higher than average probability of getting struck by neutrinos. So the second neutrino telescope that we ever built, and you can't make this stuff up, guys, it's so crazy, is known as Super Kamiokande in Japan. And it's basically a gigantic, humongous tank of thousands and thousands of gallons of heavy water. And here's a picture of Super Kamiokande so you can get a sense of just how far down the bend we've gone. There's the little Japanese technicians in the rubber raft. Here's the huge pool of deuterium-laced water. And do you see all those baubles along the edge of the walls? Those are all super, super sensitive light detectors. And they're waiting for the little sparks every time a neutrino hits it. Now, this turned out to be a pretty good way of detecting neutrinos. So, you know, everyone's got to one-up each other. Like, my neutrino detector is bigger than yours, so to speak, right? So people got thinking, how could we make an even crazier neutrino detector? We need an even bigger vat of water. Where could we get the world's biggest vat of water? Oh, I know. We could get it in Antarctica. So introducing our newest neutrino detector, known as Ice Cube, not the rapper, but the neutrino detector.
Oh, man.
And Ice Cube basically turns the entire continent of Antarctica into a massive neutrino telescope. So here's a picture of the research base in Antarctica. And what they did is they basically drilled all these shafts down into the Arctic ice. They're going to wait for the neutrinos to strike the heavy molecules inside of the ice. And they put these photosensitive digital optical modules at the base of the thing. And the funny thing about the Ice Cube Solar Neutrino Observatory is you can't detect the neutrinos from above. They first have to pass through the Earth, and then you detect them at the bottom in Antarctica. It's so insane. Today, the Ice Cube Observatory, it's kind of like a whole new branch of astronomy that's outside the electromagnetic spectrum. You're detecting ghost-like particles from space.
So if these things hit Antarctica, they will never detect it because it hasn't reacted yet?
No. The way it works is heavy water is like lead because it has an oxygen, and instead of having just a simple hydrogen attached, it's a deuteron, it's a deuterium nucleus. And you wouldn't think it counts for much, but having that extra neutron there really, really increases the probability that a neutrino will bump into it. So in Super Kamiokande, they actually just got rid of all the normal water, and they only filled it with a big vat of deuterium water, which was wicked expensive. But what they realized is if deuterium water is mixed in with normal ice, if I get a big enough volume of normal ice, the neutrinos will still hit the deuteriums that are 1 part in 6,000, and they'll still make sparks. And sure enough, they drilled the test hole down, and they put one of those photosensitive optical modules, and every time a neutrino hit the thing, it would give off a little gamma ray or something, and they would measure the gamma ray, and it had just the right energy, so they convinced themselves that they were detecting the neutrinos. Here's another cool thing. Now, you might think, well, what if these guys were just confused or something? What if they made a mistake? In 1987, while we were sitting there measuring the blips of neutrinos from the sun, we suddenly got this huge spike in neutrinos one day. It came out of nowhere, but the number of neutrinos jumped from 16 per day to like 50. And everyone stopped and went, what the shit was that? Like, what the hell caused that huge spike in neutrinos? And are you ready for this? The very next day, a massive supernova went off in the Large Magellanic Cloud. Now, I was going to save this picture for later, but because we're goofing off and riffing on this stuff, let me show you the, wait, I have to share my screen with you guys. Let me show you the before and after. So this was like a mind-blowing realization that when supernovas, when stars explode, they emit a huge burst of neutrinos, and the neutrinos actually make it to Earth before the photons do. That sounds crazy. I want to show you a picture of supernova 1987A. So here's a picture. Remember I was telling you earlier about those little dirtbag galaxies that orbit around Earth? This is one of the that orbit around Earth. The smaller galaxies that orbit around the Milky Way. This is one of them. It's called the Large Magellanic Cloud. And in 1987, that star was a star that no one had even thought to look at before, because who cares about that star, right? Then that day in the summer of 1987, they got this huge spike in neutrinos, and like a day later, that happened. Now that was an even crazier holy shit moment, because that's when we realized, damn, we're not just measuring the nuclear reactions inside the sun. This is like an early warning system for supernovae. And when one of these things goes off, you know a star is about to blow, and you can kind of like, if you can figure out where the neutrinos are coming from, you can point your telescope there and you can catch it in the act of exploding. That was the whole purpose of building IceCube. IceCube is such a big detector for neutrinos that we can triangulate where they're coming from, and the next time this happens, we'll be there to watch for it. So neutrino science is like a cool thing that's happening in astronomy. So kind of wanted to work all that into our lecture on nuclear physics because it's obviously interesting. Now, if you smush a proton, an electron, and a neutrino together, that's basically what a neutron is. And understanding the standard model of physics is understanding why you can't just simply glue a proton and an electron together. You need this extra little bit of stuff to make it all work. It's part of the four forces of nature. Obviously, for a proton to transform into a neutrino is going to be involved. The symbol for a neutrino is the Greek letter nu. That's pronounced N-U, nu. And the neutrino just, you know, I usually just represent it as a little microscopic black dot. There's one last bit here. Obviously, if you're going to go from a proton to a neutron, you're going to have to create or get an electron from somewhere. And this tends to create another very bizarre reaction that leaves behind a particle of antimatter known as a positron. A positron, the symbol of which is E with a little plus next to it, is a small particle with the mass of an electron, but it has a positive charge like a proton. This is known as a positron. And it's a form of antimatter. Antimatter is matter that has the same mass, but the opposite charge. So if you take a proton and you suddenly flip it into a negative sign, that's an antiproton. If you take an electron and turn its charge into, how do these particles transform their charge? I don't think anyone really knows the answer to that question. We just see it happening, and it's pretty cool. Do you know that in certain particle smashers, we have succeeded in creating antimatter hydrogen? We've created an antiproton, a big fat negative particle, and we've gotten a positron to orbit around it. And guess what? Just like in normal hydrogen, where it has emission lines, the antimatter hydrogen also has like similar emission lines. Very cool. Atoms, in fact, once we created antimatter matter, it got people thinking that perhaps the reaction that forms the entire universe was a spontaneous separation between matter and antimatter. And it left the tantalizing possibility that if we live in a universe where there are positively charged protons and negatively charged electrons in abundance, that perhaps there could be some other place in the galaxy or place in the universe where there was a large accumulation of antimatter, matter that has the opposite sign, but we just haven't found a way to detect it or interact with it yet. Kind of like the upside down in Stranger Things or something, right? This could be this whole universe or part of the galaxy in which large quantities of matter with all the opposite signs would exist. Now, matter and antimatter kind of function the same, with just one small catch. When matter and antimatter come together, they annihilate each other, they disappear, and they turn into gamma rays. So one of the difficulties with trying to observe antimatter is you have to kind of touch it with some apparatus, and then you immediately destroy that apparatus. It's a little bit difficult to explain, but I'll save antimatter for a different day. I've already blown your mind enough with the neutrinos. Okay, so the first step, obviously, in the nuclear physics of the star is quite complicated. And let's just review that again. You've got two hydrogens. They smush together to make a deuterium, and they leave behind a positron and a neutrino, and those guys are done. Now we're going to take the deuteron, and in step 2, we're going to smack it into a hydrogen. So our deuterium plus a hydrogen are going to smash together to create an isotope known as helium-3. Helium-3 is an unstable atom that has 2 protons, just like helium, but unlike normal helium, it only has 1 neutron, making it highly unstable. Also, this generates the production of a single gamma ray. A single gamma ray of light. It's important to stress that stage 2 of the nuclear reaction of the sun, the proton-proton chain, this stage is where all of the energy of sunlight comes from. So this, you know, if you're sitting on a beach on a sunny day, drinking a pina colada, and rays of sun are tickling your nose in the surf, every single photon striking your nose, it began its life as a gamma ray in step 2 of the proton-proton chain. This is where all the sunlight comes from. And now, in step 3, you're going to do steps 1 and 2 twice, and your helium-3 smashes into another newly created helium-3. They have to smash together right away. And they merge, excuse me, into a proper helium-4 nucleus and leave behind 2 protons as waste products, okay? So a proper helium-4 nucleus, I'm just gonna remind you guys, is 2 protons and 2 neutrons. This is the stable form of helium that you suck into your mouth to sound like a clown at birthday parties, okay? So that's just normal, good old-fashioned helium. And this is how energy is produced in the sun. Oh, you know, let's share the screen. Let me show that to you, because we're going to want to come back to this later. The book has a very, very nice diagram. I should have showed this to you right from the get-go, where they have a really cute picture of the entire reaction, and it's just very nice. Sometimes people do nice illustrations and they get it all right. I love this illustration because I think it just perfectly sums the whole thing up in an easy to see picture. So since most of you don't have the book, let me share this with you. Here you can see step 1, 2 protons create my deuteron. There goes your neutrino, there goes your positron. The positron usually annihilates with another electron to make gamma rays, but that's called pair annihilation. If you want, I can tell you about that. The deuteron slams into a proton to make your helium-3. There comes your gamma ray for sunlight. And then the 2 helium-3s slam together to make a helium-4 nucleus. The important part is this pink box. The net reaction is that you've taken 4 hydrogens and transformed them into 1 helium and 2 gamma rays. In a way, every time a nuclear reaction happens inside the sun, you are transforming the chemical composition of the universe itself. A little bit of hydrogen is shaved away, and a little bit more helium comes into existence. Over time, this enrichment of the elements changes the chemical compositions of stars, and therefore galaxies, and therefore the entire universe. All right. We had to do that. We had to do that because stars are basically balls that are powered by fusion. And in our next chapter, chapter 15, which we are launching into today, we want to understand how are other stars different from the sun? Do they all produce fusion the same way? The answer is no. The proton-proton chain is just one of a myriad of different ways that stars produce fusion. There aren't too many ways, though. It's a limited number, actually. I shouldn't have said myriad. I should have said a small number of ways. But the different types of fusion that they produce have all sorts of results that determines how long they will live, what they will do, what they will look like, why some lights twinkle blue and some lights twinkle red in our sky. So let's begin our discussion. Can I erase all this nonsense? Does everyone? All right. Let's bring things a little back down to earth here. And let's talk about stars. So in the book, chapter 15 concerns itself with stars, and this is kind of like your overview of stars. This is where you just kind of get to know your neighbors and you try to figure out what are stars like, what kind of stars do I see out there, a little bit of building up towards that HR diagram that I showed you earlier. To do this, I want to talk to you guys a little bit about how we image stars, how we take photographs of them. So allow me to get out of this slideshow here and go over to my chapter 5 or chapter 15 slideshow. And I want to sort of show you guys a little bit about, hey, when I look at stars, here's a field of stars. To your naked eye, what makes one star different than another?
The color.
The color is one. Okay, what else, Jay? I agree. Some stars kind of are red, some stars are blue, and some stars are white. That's going to turn out to be related to their black body temperatures. So usually it turns out that blue stars are hot, red stars are cool. What else can you see that's different from one star to another star?
Size.
I'm glad you said size, Joel, because it's not correct. So let me explain why. Now, if I were learning this for the first time, that would seem confusing to me, because it definitely seems to me that this star here definitely seems to be bigger than that star there, wouldn't you say? The problem is, Joel, that this is an artifact of photography itself. When starlight passes through a telescope, it undergoes diffraction. And diffraction causes the light to smear out into an artificial disk. The artificial disk is sometimes known in optics as the airy disk. Let me see if I can, I'm just trying to figure out where my damn internet is here. Sometimes my little sidebar disappears. Oh, there it is, okay. Let me see if I can, I'm not gonna be able to explain this perfectly, but I'll do my best. I wanna show you a picture of the airy disk. If you pass starlight, which is essentially a microscopic point of light, if you pass a pinpoint laser point of light through a telescope tube, it doesn't all end up in one spot, but the starlight gets smeared out into a diffraction disk. Now, you saw this diffraction before when you saw those diffraction. Remember I shined my laser through the little slits and you could see multiple laser points? What's happening is diffraction is taking some of the starlight and it's smearing out some of the starlight into these second fringes, these side fringes. But even this disk itself is not the disk of the star, but it's the pinpoint of light, the dot of light, being kind of smeared across a disk. And the size of that disk depends upon the size of your telescope. What I'm trying to say, Joel, is when we look at a picture of the sun, you can actually see the top of the sun as a distinct feature from the bottom of the sun, right? Like for instance, Joel, if there's a sunspot over here, you can see that the sunspot is there and not there. But this is not the same thing as seeing the disk of the star. This is the star as a pinprick being artificially smeared over this disk. It's an artifact of optics and photography. So what I'm saying to you, Joel, in a complicated way is it looks like F5. It looks like you're seeing a size difference in the star, but you're actually seeing something else. Can you tell me what the property actually is that makes this? It's an exposure thing, right? Imagine if you tried to, has anyone ever used the old-fashioned cameras where you can change the exposure rate? Imagine what would happen if you just left your shutter open for longer and longer and longer. As more light exposed your photograph, the star would get bigger and bigger as it started to get blown out or overexposed, right? That's like that's an overexposed image. Maybe I could share one of the young whippersnappers who never used the old-fashioned cameras will have absolutely no fucking clue what an overexposed photograph is. But back in the day, if you weren't careful about your shutter speed and you went out and tried to image pictures and you were a hack, you might produce an image that looks like this, where the shutter was left open for too long and the picture became blown out because the brightness is just overexposing all of the film, right? You don't really have this issue too much with phone cameras because they automatically adjust it using artificial intelligence, you know? So, Joel, what looked to be size was actually what property of light? Can you tell me? You thought you were looking at size, but you were really seeing differences in fill in the blank.
Distance.
Not distance, but can anyone answer that question? What is the measurable?
Luminosity?
Will, was that you?
Yeah.
Well, the only reason I object to you saying luminosity, although you're at least closer, okay? The reason I object to you saying luminosity is, Will, luminosity is the total light exposure in all directions, right? But the brightness is what you detect at Earth. You're seeing differences in brightness. And the reason why that's not the same, Will, is every time I see one star as being brighter than another star, I have a confound that I have to pick apart. For instance, in this picture here, this star, the yellow star, is brighter than this star, the white star. Everyone can see that this star, the yellow star, is brighter than the white star. But Will, I can think of two reasons why that star might be brighter to me. One is it is intrinsically more luminous, and this star might pump out more light than that star. It's a brighter light bulb. The other option is, what if this star is just way closer to me in space? If it's a lot closer to me in space, it will appear brighter, even though it's not, right? Is Sirius the brightest star in the known heavens? No, but it's the brightest star in our sky. Guess why? Because it's 8 light years away, and that's kind of close as far as the galaxy goes. So I couldn't say to you, Will, that this star is more luminous than that star. I'd have to know how close it was first. And that's the real problem with astronomy is how do we figure out how far away the stars are so that we can actually start figuring out what their intrinsic properties are? Enter the inverse square law. Let's take a look at a typical star. Let's take a look at you guys remember what the closest star to Earth is?
Proxima Centauri.
All right. Yeah, kind of. Here's the weird thing about this. The closest star to Earth is actually the closest stars to Earth, okay? Alpha Centauri, located 4.4 light years away, is actually a trinary star system that has two stars, A and B, that are about the same mass and same luminosity as the sun. And they're surrounded by a tiny little dirtbag star called Proxima Centauri. You are correct, Evelyn. Proxima Centauri made an appearance in our homework today, right? Evelyn, you're correct that Proxima Centauri is the closest star to Earth, but it's kind of by a fluke, because Proxima Centauri has this long multi-thousand year orbit around Alpha A and B, and it happens to be like closer to us now. You know what I mean? And anyways, I kind of feel like it's cheating. You are technically correct. Today, the closest star to the sun is Proxima Centauri, but I tend to think of Alpha Centauri as being the closest star because it doesn't change its distance as much. So I don't know if that's valid to you or not, but I'm explaining the issue. I think the reason why Alpha Centauri is a good one to start with is just by a magical coincidence, Alpha Centauri A, I believe, has the same luminosity as the sun, and it's located 4.4 light years away. And that means it's a good cartoon exercise for us to ask the question, how bright is a star, right? Let's answer the question, how bright is a star? We'll take as our exemplar Alpha Centauri with a luminosity equal to that of the sun, 4 times 10 to the 26 watts, located at a distance of 4.4 light years away. I'm going to quickly convert that to meters using the conversion factor from our office hours today. I didn't feel like doinking around on this, so I'm just going to do it for you. It's 4.2 times 10 to the 16 meters. And what we're going to do is we're going to bust out the inverse square law. And we're going to calculate its brightness. The brightness of Alpha Centauri is 4 times 10 to the 26 watts divided by 4 times pi, 4.2 times 10 to the 16 meters. Why don't you guys take a moment to digest that and punch it into your calculators? Any day now.
7.6 times 10 to the 8.
So,
Oh,
no.
I forgot to do it.
Did you divide? Or what did you do?
I didn't see the squared thing.
Oh, yeah. It's the inverse square law after all.
1.8 times 10 to the negative 8.
Yeah, so let's do 2. Let's just make it simple. 2 times 10 to the minus 8.
Watts.
And the units again?
Watts per meter squared.
Yeah. So, guys, the moral of that story, for starters, is stars are dim, right? If stars weren't so dim, we could light our houses with starlight, but it's amazing that we can even see that with our eyes. That's how dim they are. Our eyes can detect some pretty dim brightnesses because we can see that. Actually, Alpha Centauri, I don't think you can see it without a telescope. It's I'll show you just for funsies, just to keep this as entertaining as possible. The Wikipedia page, I want to show you guys this. It's kind of neat. This made an impression on me, so maybe it'll make an impression on you. There's a nice picture of Alpha Centauri A and B and Proxima Centauri. Check this out. Can you guys see that picture? There's Alpha Centauri A on the left. There's Alpha Centauri B on the right. And do you see that little dirt bag that they circled there? That's Proxima Centauri. If you were looking up at this field of stars, you would have no idea that that one little dot had anything to do with these two. Do you see what I mean? It's pretty confusing to know which stars are close to us. Like, you'd think, of all the stars that you can see here, the fact that this star is part of that trinary star system, you would never, ever, ever know that unless you had a way to get their distances. You'd never know. It's so confusing to figure out who's in the foreground and who's in the background. And that's kind of the problem that I'm trying to bring up here. Now, in the olden days when people would do imaging with telescopes, they actually used photographic film. And I'll show you guys a picture from history here. If we go to my slideshow, I've got a picture of Clyde Tombaugh. He's the scientist who discovered Pluto in the 1930s, in 1931. And here he is here at the Lowell Observatory, the Lowell refractor, where he discovered Pluto. And in the olden days, astronomers had to be photographers as well as astronomers. Because what you would put at the prime focus of your telescope, remember when we did the telescope lab and I had the screen and I made the little image on the screen? That's where your photographic film goes on your telescope. But it was very frustrating because you'd spend the night exposing stars to your photographic plate. And in the morning, once you were sleep deprived, here's Clyde Tombaugh with his big block of photographic plates. And he would then head into the dark room to develop the photographs and and only then could you see what pictures you got to take of the stars that evening. Today, of course, we have a much superior way of imaging the stars. We don't use photographic plates. We use these devices that are basically inside your cell phone. They're known as CCDs, charge coupled device. And this is basically how a digital photograph is taken. Each and every one of us that has a cell phone with a camera in it, there's a CCD inside of, right behind that lens in all of your photos. This is what your megapixels is referring to, how many millions of pixels your CCD camera has. CCDs are basically little wafers of silicon where photons of light come in, knock into some kind of silicon barrier, and kick electrons off into a bucket that is then bucket brigaded out the side of the CCD chip and read by your computer. You can think of it as like a computer screen in reverse. Instead of the pixels pumping out the light, the pixels capture the light and turn it into an electronic signal. CCDs are so efficient at detecting light that good ones can detect 99.9% of all photons that strike the surface. That means, and now compare that to photographic film. You know what percentage of light photographs capture? Like 15%. And your eyeballs capture like 9%. Like 9 out of every 10 photons that hits your eye is not detected. They're just heat up your eyeball goo or something. In photographs, it's 85 out of 100, or 15 out of 100 that's detected. But CCDs basically capture 100%. They capture every single photon. And that means you can actually count the radiant flux, like that number of watts per square meter that we just measured for Alpha Centauri. You can capture all 2 times 10 to the minus 8 watts per square meter at your detector. Here's what a typical backyard astronomer setup looks like. You've got your big telescope, okay? This guy's got a little dome in his backyard. You can see he's pimped it out pretty nice here. And this guy's got kind of a cool rig because what you can see is he's got an eyepiece attached to it so that he can put his eyeball up and look in and kind of check out the stars that he's looking at. But he's got a little rotating knob with a 45-degree pickoff mirror. And if he wants to image the galaxy that he's looking at, he can flip this over, and the CCD chip is inside of this cooling unit. They have to cool them so that infrared photons won't create noise. And basically this goes right to the computer and he can sit there taking mind-blowing pictures of space. You know, a lot of these pictures of space that you see in the magazines and the covers, like nebulas unveiled. Okay, some of them are taken by the Hubble Space Telescope, yeah, and some of them are taken by the Keck telescope, but most of those are trying to do research images, which are just grainy blobs. The people that take those mind-blowing pictures of space are often grumpy old men out in the deserts of Arizona that are just sitting there on their porch with a cigarette and a cup of coffee, and they just stay up all night with these small telescopes, just imaging the stars and being grouchy, and then like producing the pictures the next day. And I say grouchy old men because at one point I wanted to learn some astro imaging chops, so I went to one of the biggest forums there, the Northeast Astro Imaging Seminar, and it was in upstate New York, and I just went to see what was up and see what techniques the astronomers had there. And I think there was like 100 people at this conference, and of the 100 people, there was one woman, and it was the organizer's daughter who was there. But the rest were just these like grouchy old dudes that were like, yeah, check out these shots of Andromeda that I got last night, or check out my, you know, everyone's got their iPad, like check out my comments, you know. So why do I mention this to you? Because astronomy is this science, and there are all these eggheads building neutrino detectors, but there's this whole other side of it where it's the amateur astronomers have got these pretty badass telescopes, and they're out there every night with their CCDs just taking mind-blowingly cool pictures of space. So 9 out of 10 times, those astronomy pictures of the day that you're seeing, they're just taken by people who are kind of just out there for the thrill of it all. You know what I mean? All right, now, why am I telling you this story, besides the fact that it's entertaining, is one never needs to actually calculate the brightness of a star. Because why would you calculate the brightness of a star if you could just go out with your rig and you could take a picture of it? That's how you measure the brightness of a star. You measure the brightness of a star. You know, in the old-fashioned days, like when Clyde Tombaugh was doing it, they would actually produce photographic negatives. I'm old enough where the first pictures of space that I learned on, we actually had photographic plates at BU. That's how old I am now. Let me show you photographic negative astronomy, or just, so sometimes you wouldn't even develop the positives of the image. This is exactly what the old photographic plates of stars and galaxies would look like. You'd have something like this, or here's a galaxy right here, right? This is a perfect example. And the way you would actually measure the brightnesses of stars is you'd have your photographic plate, and you'd actually take out your bloody ruler, and you'd have some conversion like this. If the star diameter is 5 millimeters, that many millimeters corresponds to this many watts per meter squared. And you would just measure the brightness. I think in some cases what you would do is you'd surround them with a circle, and you'd be like, okay, this star is 4 times brighter than that star, and then you'd have a conversion to, that's how you would measure brightnesses, with a ruler, and you'd measure them on the page in millimeters. Now today we have a slightly more sophisticated method of doing it. Because we're doing all this by computer, the computer actually measures the amount of light you're getting from each star. Here's where we bring it back to the classroom. I know we're going to do some tea breaking soon, but there is no point to this version of the inverse square law. It's what we teach our students because it's easy to digest, but one would never calculate the brightness of a star because it's a measurable. It's something that you can actually get from your telescope. In astronomy, we call it the observable. That's kind of like a catchphrase in science. The observable is the thing that you actually observe with your detector or your apparatus. But then there's things that you want. And you want to know what you want? The same thing that everybody wants. When I take people to my telescope and I show people pictures of the Ring Nebula, or not pictures, when I show them the Ring Nebula through my telescope, you want to know what the first question every person asks me is? Whether it's a grandpa or a little kid, they all just say, how far away is that? That's what they want to know. How far away is that thing? Well, that's a damn good question. And it turns out to be that how far away is that thing is one of the hardest questions to answer in astronomy. That's where the inverse square law comes in. So this formula, of course, is the inverse square law. But when I rearrange it and solve it for distance, I come up with the so-called luminosity distance formula. And that is D is equal to the square root of L over 4 pi b. And I want to explain what this is trying to say to you in math, and I want to explain it in words. It's a three-part argument. I can measure B, say with a CCD. If I could somehow, if I knew what the luminosity of the star was beforehand, then I can compute D. And that's what I want. I want to know the distances to the stars. Unfortunately, I can't measure the distance to Alpha Centauri with a tape measure. They haven't built one long enough yet. So I'm stuck using the luminosity distance formula. It does, however, raise a small conundrum. The conundrum that I tried to explain to Will. How the hell can I know the luminosity of a star, right? I don't have Dyson spheres at my disposal. As I pointed out to Will earlier, the luminosity of a star, actually, I'm going to save this picture before I forget, because this is just a fantastic plate, and I'll never find it again. Photo negative. I think that's galaxy. Bear with me, guys, because this is important enough. I'll forget that I saved this two weeks from now, but all right, there we go. Probably 2 seconds from now. As I explained to Will a little earlier, in this slide, to know the luminosity of a star would require us to be able to somehow be able to measure all of its light output. So this is going to sound like a little confusing, but the third method, the method of finding the luminosity of a star, is to solve this formula here. The luminosity is 4 pi d squared times b, the brightness. And what I'm actually going to do is I'm going to measure the brightnesses of stars, and I'm going to focus on stars that are close to Earth, like Alpha Centauri. And I'm going to get their distances through other trickery. Then I will compute their luminosities. And then anytime I find a star like Alpha Centauri, I will be able to put it into this equation and get their distances. People sometimes describe astronomy as kind of like building a tree fort. Each platform that you build gives you a place to stand so you can build the next platform to get up to where you want to go. It's sometimes referred to as the cosmic distance ladder. First, I figure out the distance to the sun. Then I use the sun to figure out the distance to Alpha Centauri. Then once I have the distance to Alpha Centauri, I can figure out the distance to Sirius. Then I can figure out the distance to the center of the galaxy. Then I can figure out the distance to Andromeda. Then I can figure out the distance to the radius of the universe. You know what I mean? You're trying to build your way up, and this is what this story is all about. I think this would be a good place for us to pause. Afterwards, we'll talk a little bit about parallax and some of the techniques we use to find stars in our local solar neighborhood. So let's take some time to chill. Don't let me forget that, I'm going to pause the recording in a second. Don't let me forget that we need to do our final homework problem before it's lab time today, okay? Okay. I almost fell asleep on that one. I sat down in the chair and I thought, ooh, this feels too good. Okay, got a lot of ground to cover. Not sure how I'm going to do it all. let's get down to how we find the distances to some nearby stars. Let's talk about a technique called parallax. So if I start by showing you guys some slideshows, I want to tell you that there's this concept called our local solar neighborhood. These are the stars that are closest to the sun in space. And you guys will notice that these stars are, where's the sun here? Here we go. These are stars that are pretty famous stars that you've heard of before, or at least that I've heard of. Some of the brightest stars in the sky are the stars which are the closest to us in space. Procyon is in the constellation of Canis Minor, the little dog. And Castor and Pollux, they're part of Gemini. Vegas and Lyra, Fomalhaut, these are famous stars. Denebula, these have well-known names because being closer stars to us, they tend to be the brighter stars in our sky. And these are stars that are within, you know, a few hundred light years of Earth, or the sun rather. Astronomers call this your local solar neighborhood. And these are the stars that we have the easiest time measuring the distance to, and we focus on them first. The technique that we use to measure the distances to nearby stars is called parallax. And parallax is an angular shift in the position of nearby stars due to the motion of Earth. So it only works if you focus on stars that are close to Earth and you compare them to slightly more distant stars. As Earth goes around the sun, they shift their angular position with respect to the background stars, and we can actually use geometry to measure that angle and to calculate the distance to the star. So this is what it would look like if you could stare at a field of stars for a full year while Earth goes around the sun. You would see that some of the stars undergo dramatic angular shifts because they're close to us. This is their parallax shift. And other stars, like these ones here in Orion, are so far away that they're more difficult to measure the parallax shift for. Usually you measure it on the sky by measuring changes to your right ascension and declination, and you measure these shifts in some number of arc seconds. Let's draw the picture on the board and see if we can't make some wild sense of it all. Here we go. So introducing parallax, an angular shift in the positions of nearby stars due to the motion of Earth. It's a technique used to find distances. All right, so this angle rho is going to be known as the parallax shift, and it's always measured in arc seconds because the angles tend to be very, very small. And we can make a note that it's used to find the distances to stars. That's the whole point. Let's draw a nearby star in red. And we will draw over here the sun. And we'll draw Earth at some different points in its orbit. And rather than wait 6 months apart, I'm going to focus on a 3-month interval where the Earth goes from this position, which might be, I don't know, October, to this position, which might be January. And somewhere off in the distance, I'm going to see a vaguely familiar looking constellation that does not undergo much of a parallax shift because the stars are pretty far away from each other. Okay. So in October, I look out at the star and I see its position somewhere near the sword of Orion. And I check this star out again 3 months later, and I see it's shifted to somewhere down near the foot of Orion. Now the parallax shift is this angle here. That's what I'm measuring, rho. But you'll notice by an old-fashioned theorem in geometry, alternate interior angles, that rho happens to be also equal to the angle that is made between the sun and Earth as seen by the distance to that star. Now, normally what I would do is I would apply the small angle formula to this problem. Here, S is the separation from the sun to Earth, D is the distance, and rho is the parallax shift. And if I use the small angle formula, that's S equals, let's see, here it's rho times D over 206,265 arc seconds. And here, S is permanently fixed at 1 AU, because that's the radius of Earth's orbit. If I wanted to solve for the distance, I would get that the distance is equal to 206,265 arc seconds divided by the parallax angle times 1 AU. Class, if I measure my parallax shift in arc seconds, what units will my distance come out to be in?
AU.
Say that louder, Laura.
Would it be AU?
That's right. Would you say that AU are a particularly good distance to use to measure the distances to stars? Sorry, is that a good unit to use to measure the distance?
No. Should it be light years?
Light years would be more tasteful, wouldn't it, right? I wouldn't want to measure the distance between Providence and Boston in inches. That would be a little bit awkward. But let me tell you what, Laura, although light years would seem to be the best unit, that's not going to be the unit we're going to use. Because astronomers are so damn lazy, myself included, that they tend to not even want to convert from astronomical units to light years. That's too much work for them. And they kind of invented a new unit of distance just to avoid having to do unit conversions. When I think about the art of designing a unit, I think of inches and feet and meters and kilometers. Of all the units that we use to measure distance, maybe one of the most useless, in my opinion, is the yard. And hear me out on this. Why I think the yard is the most useless distance, a yard's kind of similar to a meter, right? Is that a yard is equal to 3 feet, right? So anything that you could measure in yards, like the length of a piece of fabric, you could just as easily measure in feet with no significant change in the size of the number, right? Like 2 yards of fabric is 6 feet of fabric, whatever, no big deal. With that in mind, allow me to introduce to you a new unit of distance, a unit which is essentially a space yard, okay? And that unit is called the parsec. Introducing a new unit of distance. It's known as the parsec. And 1 parsec is defined roughly as 3.26 light years. Oh, sorry. Now, the actual definition of the parsec is weird. It's the distance at which 1 arc second subtends 1 AU. In other words, make a tiny little 1 arc second angle and stretch it out into space until the separation between the arms of your triangle there is 1 AU. And if this angle is 1 arcsecond, you get to 1 AU after 1 parsec. Now, at this point, you're thinking, WTF, why in God's great earth would anyone design such a distance? What's the use of it? Well, get ready for this sleight of hand. The entire point of designing a parsec is so that you get this one particular conversion factor. 1 parsec happens to be equal to exactly 206,265 AU, which you'll notice is the same number that appears in the small angle formula. 206,265 is kind of a magical number in physics and astronomy. It's technically speaking, for an advanced student, the number of arcseconds in 1 radian. A radian is another unit of angle you've probably never heard of before. The usefulness of it is that you can use this number to quickly compute distances to stars. Watch what I'm about to do here, guys. I'm about to perform a unit conversion so that instead of measuring the distances to stars in AUs or even in light years, I'm going to do dimensional analysis and I'm going to convert to parsecs. So I'll put AUs on the bottom and I'll put parsecs on the top. 1 parsec is equal to 206,265 AU. Not only do the units of AU cancel out, but also the 206's 265 cancels out. And I end up with probably one of the greatest and easiest formulas in all of astronomy. The distance to a nearby star in parsecs is simply the reciprocal of the parallax shift in arcseconds. I can quickly calculate distances by just measuring a parallax and flipping it. For instance, since Alpha Centauri is one of the closest stars to the sun, if I went out for Alpha Centauri, I would discover that its parallax shift is 0.74 arcseconds. If I plug that into my distance formula, 1 over 0.74 arcseconds gives me approximately 1.35 parsecs, which is approximately 4.4 light years. Hey class, what does it mean if the closest star to Earth has a parallax of 3/4 of an arcsecond?
Everything's really far away.
Yeah, and that's kind of my point, Will. Things are really far away, but also parallaxes are wicked freaking small, right? The largest parallax that's you can even observe, Alpha Centauri, is less than 1 arcsecond. The parallaxes of most stars are incredibly tiny. Like, for instance, if I share a screen and I just go to the Wikipedia page for a star like, I don't know, Sirius, I bet it will list its parallax shift. They tend to do that over here on the right. That's 380 milli-arc seconds. That's basically 0.38 arc seconds. That's damn tiny. What's the best telescope in the world plus a little bit above the world? Best telescope in the world.
Hubble?
Hubble. Do you remember what the angular resolution of Hubble was due to diffraction?
No.
No.
Like
It showed up
0.5.
briefly in our homeworks.
0.5, wouldn't it?
0.5 arc seconds. Very good. I'm going to erase here. Any objections? Let's try a sample problem. What is the most distant object that Hubble can measure the parallax shift for? So the alpha minimum for Hubble is 0.05 arc seconds. So let's assume that that's the tiniest parallax shift we can measure. In that case, Hubble can measure distances out to, what's 1 divided by 0.05?
0.5?
No, it's 20, right?
Yep.
520s make a $100 bill, right? Okay. That's 20 parsecs. Assuming that a light year is assuming that a parsec is a space yard, roughly how many light years is that? Loosely speaking.
$65.
Yeah. Something like 60 light years, 65 light years, whatever. I'm just pretending it's a space yard.
Okay.
Now I'm going to show you guys a picture here. If Hubble, the best telescope in the world, can see parallaxes down to 0.05 arc seconds, what fraction of the Milky Way galaxy, hold on a second, I got a problem here. What fraction of the Milky Way galaxy can Hubble explore using the parallax technique? Here's the whole galaxy, right? How far does 60 light years get you?
Twice as far as that.
Huh?
Twice that.
No, it's 30,000 light years to the galactic center.
Wait, we're at
Compared to
65 light
30,000
years?
Huh? Yeah, that's like 65 light years, right?
That's barely out.
So what fraction of our galaxy can we explore with parallax?
Almost none.
0%. Yeah, pretty much. That's the point, right? Parallax doesn't seem to get you very much. The truth is that Hubble can actually do a little better than 0.05 if you use a special technique called spatial scanning, but it's a little much to get into. Let me find my slideshow really quick. So I think for years, I can't remember exactly how far you can get. This is a little bit of a lie. You can actually do a technique with Hubble to get you a little past 60 light years, but I won't go into that in the interest of time. When I was a student, they had designed a satellite at the end of the 80s whose only job was to measure parallaxes so that astronomers would know the distances to as many stars as possible. Now, the engineering of it was pretty clever, but they somehow managed to get resolutions less than what Hubble would get. They got down to 1 milli-arcsecond. And that allowed them to measure distances out to 3,000 light years. And that allowed them to have a catalog of known distances to about 100,000 stars. And you got to understand and appreciate what this means. Every single research paper in astronomy, every single science experiment depended upon people accurately knowing the distances to these 100,000 stars. So when I was a student, every single paper that was published always had to reference the Hipparcos mission because everyone depended upon this table of values. But getting out to 3,000 light years, 100,000 stars sounds good, but that's only a small fraction of the Milky Way. So we had to use more exotic tricks to figure out how distant objects like Andromeda was. We had to use trickery, some of which I will teach you. But the cool thing that's happened today is we've invented a new satellite whose only job is to measure parallaxes. And it launched last year, and its name is the Gaia mission. And this is, you know, average Joes don't know about it, but this is a big deal in astronomy. Astronomers freak out about this. It kind of changed the game. First of all, what's cool about it is this satellite was famous for developing the world's biggest CCD camera, a 1 gigapixel CCD sensor. Here you can see the technicians working on the thing, right? A huge chip by comparison to others. And by using like advanced engineering and random trickery, and they put this satellite at a Lagrangian point. It's in a gravitational equilibrium between the Earth and Sun's orbit. So it's kind of far away from Earth, and it just scans the stars, measuring their parallaxes. They can measure parallax shifts of 10 micro arcseconds. So let's think about, do you guys remember what a micro is? What's a micro? A micro. Did I spell that right?
Yeah.
I'm sort of sleep deprived here. Yeah, got it. Okay, I just had a paranoid moment. If Gaia can get parallax shifts of 10, a micro arcsecond is 10 to the minus 6. That's what micro means. So that's essentially 10 to the minus 5 arcseconds. That gets us out to a distance of 10 to the 5 parsecs, or about I guess, what is that, 300,000 light years? Basically, Gaia can measure accurately the distance to every star in the Milky Way galaxy, and it can even get the distances to some of the stars in the Large and Small Magellanic Clouds. So important was the publication of this satellite's data that overnight all the parameters of astronomy changed and increased their precision. For instance, the age of the universe changed overnight, the radius of the universe, and Gaia has allowed unprecedented precision. It increased the precision of all our astronomical measurements. I mean, think about this, guys. People today are debating about the age of the universe down to the 5th significant figure. Watch this. Oh, I was expecting Google to give this to me. Look at this right there. 13.799 billion years old, plus or minus 0.02 billion years old. So people aren't even arguing about whether it's 13 billion or 14 billion. They're arguing about whether it's 13.79 or 13.77 billion years old. You see what I mean? Like that's a pretty robust confidence in your ability to measure the age of the universe. And it's because of satellites like Gaia that we have increased the precision of much of our cosmology. So it's just kind of a cool thing that's a current event. Parallax is still a very important technique. It's how we get the distances to nearby stars. Do I want to do the magnitudes? I talked to you guys a little bit about the magnitude system. I guess I have to before I talk about the Hertzsprung-Russell diagram. I just want to reintroduce magnitudes to you. I've got a bunch of little things to teach you before I can get into our lab on binary stars today. Let's do a little review of the magnitude system, which is a sort of classic way to measure brightnesses of stars. It's going to seem like I'm jumping around a little bit, and I kind of am. I've got to do a bunch of unrelated modules with you guys, and then I'm going to tie them in later.
Oh yeah, we got to do that homework question too.
Yeah, that's what I'm kind of paranoid about. I think I'm just going to go into note mode for a little bit and try to keep the fun stuff out of it. I'd like to introduce the magnitude system. The magnitude system is a way to measure the brightnesses of stars by nothing more reliable than the human eye. And it was invented by a Greek astronomer, Hipparchus, in God knows what, like 500 BC or something, Hipparchus, maybe 300 BC. He was an ancient Greek astronomer. And a magnitude, when you talk about numbers, you know, if you have something like 5 meters, this is known as the magnitude, the raw number, and meters is considered the unit. So the fact that we call this the magnitude system means it's supposed to be a unitless ranking of the brightnesses of stars. And this could be kind of like your top 5 favorite movies. This movie gets a number 1. This movie gets a number 2. This movie gets a number 3. It's just a ranking, a number system. Like it's kind of like amihotornot.com for stars, okay? That's a number 5. That's a number 6, okay? So what we do is Hipparchus broke the stars up into 6 ranks originally. And a magnitude, now by the way, little m is our symbol for what's called apparent magnitude. So a magnitude of 1 would have been the very brightest stars that you could find in the sky. And then as they got to bigger numbers, they got dimmer and dimmer, all the way to an apparent magnitude of 6, which was like just the faintest star that Hipparchus could barely see with his eye. Because Hipparchus designed this hundreds of years ago, he didn't take into account all the stars in the sky. Also, we had to make an adjustment at some point because, for instance, on the magnitude system, the star Vega has an apparent magnitude of 0 because it's even brighter than some of the stars that he was choosing. And the brightest star in the sky, Sirius, has an apparent magnitude of -1. Dang. Even more annoying, you can measure the magnitude of the sun or the moon in this system. The magnitude of the sun is like a -26. And I forget what the magnitude of the moon is, but it's like a -12 or a -11, something in that range. Oh, thank you. I could definitely use that. Brain juice. So obviously he did a bad, right? If he'd only made, actually any way you cut it, this is going to be an awkward system. The magnitude system essentially is a logarithmic, remember the logarithm chart that I showed you earlier? The human eye weirdly has a logarithmic sensitivity to light. And that means if you ever had a math class where you had to graph log x as a function of x, the graph of log x kind of looks like this. It looks like a hill. So if you look at a star that's twice as bright, or if you look at a light bulb that's, if you look at a 200-watt light bulb and you compare it to a 100-watt light bulb, your eye doesn't detect the 200-watt light bulb as being twice as bright as the 100-watt light bulb. You only detect it as being 1.5 times as much, because for every increase in brightness, your eye kind of saturates and tapers off. Your eye has a logarithmic response to light. That's what we say. It turns out that this is annoying, but it's useful, and that's why we continue to torture students with it today. So the big idea, by the way, just so you can get a sense of why astronomers got stuck with this, we've been measuring the brightnesses of stars for thousands and thousands of years. I told you I wasn't going to entertain you at all, but I lied because I can't help myself. I want to show you guys some really beautiful art meets science kind of stuff. I used to love having this as my computer screensaver, but I've neglected it over time. But there are these two really beautiful 1800s atlases of the stars that were published a couple hundred years ago, and they're so mesmerizing and beautiful. There's the Flamsteed Celestial Atlas and the Jameson Celestial Atlas, and they're both available on the Navy's website. Hold on, I think it's the Jameson Celestial Atlas. They have high resolution plates, and guys, you gotta see these. They're so cool. There's the Jameson and the Flamsteed. I think it's the Jameson one is the one I like. So let me just show you like a picture of Taurus. This is plate 14 of Taurus. And look how beautiful this celestial atlas is. First of all, notice how some of the cool things that we've learned in our class are coming together in this beautiful artistic sense here. Notice they're plotting the right ascensions and the declinations, the coordinates of the stars that you learned about. And if I can zoom in here, let's look at how they've done the magnitudes of stars. I think the first rank magnitude stars, they get like a 5-pointed star with a circle in it. And then the second rank magnitude stars are like a triangle. The third rank magnitude stars are here. And then these are like 4th or 5th magnitude. I think down at the bottom, they have a little legend in one of the plates. Not this one, I guess. One of the plates contained a legend with what the rankings of stars are. Let's see if we can find it here. Look how beautiful these are. They make really cool screensavers. Just some classy art, some classy, some really talented illustrator just tried to make a faithful reproduction and represent the magnitudes. This was done in the 1800s, I think, right? So you realize the magnitude system goes back older than science itself. I just remember I looked at this recently, and one of the plates has a legend. Oh, here's Orion. Come on. So I know that the belt stars are a second rank magnitude star. So it looks like our second rank magnitude stars are sort of like this. Betelgeuse would be a first rank magnitude star. So would Bellatrix. So they have slightly different shapes. Just really cool, you know? I like it because in addition to the major constellations, there are minor constellations like Lupus, the bunny and stuff, and he included all of those and the little astronomical tools and things, Fornax. It's just fucking awesome. Just a cool art meets science thing that I'm really down with. So part of me showing that to you is so that you could get inspired to go and check it out yourself. And if, you know what the hell, I'll put the link into the, I'll put the link to these plates inside the chat log. So if you guys are inspired, you can go and kind of click on them yourself. But also to impress upon you that the magnitude system has been around for a long time. And it's useful because it's a simple way to represent the intensities of stars. Okay, so what do I need to teach you? I need to teach you that there is a conversion between brightnesses and magnitudes, and it's kind of a big deal. You got a little taste of it in your in your office hours today, at some point, someone discovered that if you go from a magnitude 1 star to a magnitude 6 star, that was a change of 100 times in brightness. In other words, in the magnitude system, a change in magnitude of 5, there's no real units for magnitudes, but I could say a change in 5 magnitudes, would be a flux ratio of 100 in terms of light output. So that the brightness of star A to the brightness of another star, star B, is 100 raised to the power of the change in magnitudes divided by 5. That's how you do this. Oh, sorry, that's from homework today. The change in apparent magnitude divided by 5. That is 100 times magnitude B minus magnitude A divided by 5. If you solve for the magnitudes, you get a log of the ratio of brightnesses. That's where the logarithmic comes from. Now, if you thought apparent magnitudes were weird, oh, I got an idea. Let's try this. How much brighter is a magnitude 1 star like Betelgeuse versus a magnitude 2 star like one of the stars in the belt? And I'd like to point out to those of you who forgot what the real deal looks like, this first slideshow of mine, slide 1, or lecture 1, started off with a picture of Betelgeuse. So over here, here's Betelgeuse. That's like a first rank star. And next time you see Orion, which won't be until the fall, I guess, notice that you can clearly see that the belt stars are kind of like a magnitude 2. The sword stars are, at least these guys are pretty good examples of a 3rd magnitude star. 4th magnitude would be like this. And 5th and 6th magnitudes would be like a 6 magnitude star. By the way, you know how in Providence we're pretty light polluted? I can see down to a 3rd magnitude star, but I cannot see a 4th magnitude star. This star, and this star are completely invisible from Providence's sky. I'm guessing if you go to Block Island, you could see a few of the fainter ones. But the places you have to go to still see a 6 magnitude star are like the deserts of Arizona. Maybe in Iraq or Afghanistan, you guys might have seen some stuff like that. In a very, very dark desert sky, you could see that. But in Rhode Island, forget about it. How much brighter is a magnitude 1 star versus a magnitude 2 star? I'd say the ratio of a brightness of magnitude 1 to the brightness of a magnitude 2 star is 100 to the power of 2 minus 1 divided by 5, which is 100 to the power of 1/5. I'm guessing you guys forgot this from your math class, but to raise 100 to the power of 1/5, that's the same thing as the 5th root of 100. So you guys remember how to take your arbitrary root key. It's the opposite of the x to the y key. So let's take our calculators and let's do, which finger? This one. Okay. 100 raised to the power of, oops, sorry, let me try that again. 100 shift arbitrary root 5 equals, it's a factor of 2.5. In other words, the stars in Orion's belt are 2.5 times dimmer than Betelgeuse. All right. if you liked that, you're going to love this next bit. At some point, people got so jazzed up on apparent magnitude that they decided to further extend the concept, and they decided to invent apparent magnitude is like a tracer of the brightnesses of stars. And they started asking themselves, could I do this for the luminosity of stars? You sure can. Introducing absolute magnitude. Absolute magnitude is the apparent magnitude that a star would have if all the stars were pushed to the arbitrary distance of 10 parsecs from Earth. In other words, imagine every star is at the same distance from Earth, arbitrarily chosen to be 10 parsecs. And then you look up at the nighttime sky to see how bright they are. Whatever their magnitudes would be, that's known as their absolute magnitude. Yep, that probably sounds as confusing as it is. Let me write it down for you. The concept in astronomy is that apparent magnitude is a measure of the brightness of stars. And absolute magnitude, which I'm going to use the symbol capital M for, as is tradition, is going to be a tracer of the luminosities of stars. So the absolute magnitude is equal to the apparent magnitude a star would have, put some asterisks next to that, a star would have if it were located at an arbitrarily chosen distance of 10 parsecs. Now, I almost thought about skipping this and not teaching it to you, but it turns out that there's a number of things that we're going to be doing in our class that depend upon this. Don't ask me to explain it all now, it's too much. I think a useful chart here could be made to help you understand the differences between them. And I like this slide here. This slide really sums it up in a nutshell. You all know that the closest star to Earth is the Sun, and its apparent magnitude is stupidly small. It's -27. By comparison, the red star Aldebaran, in Taurus the Bull, it's got a magnitude of pretty close to +1. But if both Aldebaran and the Sun were moved to the same distance of 10 parsecs, the magnitude, of the Sun would be a +5, and Aldebaran would be a -1. Let's take that as a quick chart. So comparing the Sun to Aldebaran, the apparent magnitude is -27 versus +1. The absolute magnitude is a +5 versus a -1. Which star is brighter on my sky? That's supposed to be the easy question.
The Sun.
Which star is intrinsically more luminous? Which star pumps out more light?
Aldebaran.
Yeah. based on what I've done so far, the next part of our lecture would have been very, very interesting. But because it's the end of our lecture day, getting very, very close to it, and we're getting fatigue, I'm going to save that juicy morsel on the story of the HR diagram. I will save it for our next class, okay? But I do need to do binary stars with you. That way we can start off next class with some really fun stuff. Today's lab is a lab on binary stars. So what I'm going to do is I'm just going to skip ahead, and I'm going to introduce binary stars as a concept to you, and we're going to crank out our homework problem real fast, and then we're going to crank out our lab on binary stars fast. That's the plan. So let's just devote the rest of our day to binary stars so that you can learn about why they're so important in astronomy. So I'm going to do maybe a quick module, then we'll solve the homework problem, and then we'll do our lab together. They're all these three things are going to be related to each other. Let me just, oh, do we have paper towels? Awesome. Can I just want to clean my board. Class, my board is getting so gicky that you can't see it on your screen here, but I need to kind of wipe it down. I can see it actually starting to ruin my marker, and I have to keep paying for them, so I'm trying to keep myself squeaky clean here. Okay, when you look at a field of stars at night, most of the time you're thinking to yourself that, what number is this? This number is 94. Holy cow, that's a big slideshow. You're thinking that most of these stars are individual twinkling points of light or balls of plasma. But you would be surprised to discover that binary star systems constitute half of all stars that you see in the sky. Half of all the stars in the sky are binaries. And this leads to a funny joke. I'm going to put funny joke in parentheses there. In astronomy about binary stars. The joke goes, 3 out of every 2 stars is a binary. And as you saw in the case of Alpha Centauri, under extreme circumstances, even trinary star systems are possible. Hell, binary star systems, trinary star systems, y'all ever heard of globular clusters before? Globular clusters are clusters of stars. Why can't 92? A globular cluster is a nest of stars. These things orbit the edge of our galaxy, and globular clusters contain hundreds of thousands of stars that are all swarming around each other, all on Keplerian ellipses in a giant spheroid. Globular clusters are really weird structures, and I love showing them to people when they come to my telescope because they look cool. When you look at them through a telescope, at first it looks like a kind of fuzzy comet, and then your eyes start resolving all of the stars, and they're all dim and red, and they just look pretty cool. Laura, Shay, did you ever get to come out to my telescope when you took the class?
No, I didn't.
No.
That's a tragedy. We got to fix that at some point, guys. Well, globular clusters are the coolest. All right, you got to trust me on that. Anyways, multiple star systems are possible, and it turns out that multiple star systems are useful to us because if you had to take a guess, let's just see how you do this. Of the the 4 key parameters of a star, mass, luminosity, radius, and temperature, which one do you think is the most important? And I mean most important in determining the star's life, its evolution, what it looks like. What's the most important property of a star? If you had to pick one of these, I bet you guys could just guess which one it was intuitively. The sun's lifetime is 10 billion years. One of those parameters plays a much bigger role in determining it than any other.
The
The
mass.
mass.
Exactly. I don't even have to teach you anything, and you knew that. The mass is the most important, but here's the difficulty. Yes, mass is the most important, but guess what is the hardest to measure?
The mass.
Exactly. And that's because you don't have a Stop and Shop scale that you can go and dunk Sirius onto, right? You're basically, by the way, all of these parameters, you can get all of these just by spectroscopy. You can analyze the absorption lines of stars and you can figure out all the rest of it. But the mass is the one most difficult, besides distance, mass is one of the most difficult properties. It turns out that the point of binary stars is to determine the masses of stars. We can find many properties of stars from binaries, but the principal job of a binaries is for us to find the masses of stars. In fact, so important is this as a concept that when stars do not have a binary companion, we often have huge uncertainties as to what their mass is. As a visceral demonstration, allow me to share with you the star Betelgeuse. Let's just go to its Wikipedia page, which usually does a pretty good job of quoting the most recent research as to the parameters of the star. Betelgeuse, I happen to know, is just a perfect example of a not binary. By the way, I want to tell you guys a funny anecdote really quick. 2 summers ago, I was teaching a summer class just like yours, and I had a set of twins that took my class, and they were absolutely adorable. They were cute, they had great personalities, and they were great students, and they were just funny people to have in the class because they did funny twin things that made you go, aw, right? And I didn't get too much in their grill or anything. I stayed professional, but I was, you have questions about twins because it's curious. It's a curious thing, right? So at some point they like to talk about it. So I was like, what's it like being a twin? What's the etiquette of it all? And the first thing they said was, well, don't ask, are you twins? Because duh, obviously we're twins. But the nice, polite thing to say to twins is, okay, who's the A twin and who's the B twin? I guess the A twin comes out first and sometimes has slightly dominant characteristics. Also, apparently they would go to this twin festival in Ohio every year and do like a talent show with thousands of twins. It was hilarious. And so one day they're talking to me and they were like, you guys think being twins is weird, but we think being twins is normal, and we feel bad for you guys that don't have a twin. They were like, you want to know what we call you guys? And I said, what? And they're like, we call you guys singletons. It got me thinking, why am I telling you this story? Because binary stars are so common in star systems that I needed a name to describe single stars. And that's when I realized, okay, that's what I'm going to call single stars from now on. They're singletons, okay? So Betelgeuse is a great example of a singleton. And because it's a singleton, we are not able to determine its mass to a high degree of precision. So I want you guys to look at the latest results here from Wikipedia. they quote the mass of Betelgeuse, they've got the reference paper right here, as being 12 solar mass units plus or minus 5 solar mass units. So in other words, the mass could be anywhere from like 7 solar masses all the way up to 17 solar mass. You know what I mean? It's a huge range in the uncertainty, because unless your star is part of a binary, it's really, really tough to measure the mass. You have to use weird tricks. Like I was just noticing this paper, measuring the mass of Alpha Orionis from stellar limb darkening. Give me a break. Bring a book, okay? That's not an easy way to do this. The right way to do it is to find yourself a binary, okay? And the formula that we use for masses is, of course, NK3, the cosmic balance beam, as it's called. And it's the sum of, our two masses, our M1 plus M2, is 4 pi squared A cubed over GP squared. Now, do you guys remember what I don't even know if you remember what these symbols mean, much less their units. M1 and M2 are obviously the total mass of the system. Do you guys remember what units we used for A and P?
Years in AU. I mean, shoot. No.
Offset, focal point. I'll just keep saying things.
Okay, hold on. You need a diagram then. Let's go back to slide 92 for a second. I think somewhere here I have a diagram of, yeah. So in this binary star system, I should have used M1 and M2, but the day I made this, I used big M and little m, whatever. It doesn't really matter. A is the distance between the two stars. That's the radius of orbit. And P is the period, right? But I need you guys to remember that the units that you quoted at first, Laura, were Keplerian units. This formula uses MKS units. So my A would be measured in
Kilometers.
Kilometers.
It's not the KKS unit, it's the MKS unit. The K in MKS
Meters.
stands for kilograms. Yeah, so meters.
Okay. And then seconds for the period.
Very good. And then the masses would be in kilograms.
Right.
Normally what you try to do in binaries is you try to measure their period, which is usually the easy thing to do. You try to measure their separation, which is less easy but doable. And then you calculate the masses. In other words, if I can watch stars orbit around each other, I can figure out how massive they are. But Laura, it's interesting that you mentioned AU and years. That was the Keplerian version. But
And that was based on the sun, right?
Yeah, and it turns out that I first introduced this version of the formula to you guys because I kind of wanted to beat you up a little bit and make you get good at math. But now, presuming that you're good at math, I can tell you that there's a cheaper, simpler version of this formula that uses the units that are better for dealing with stars. So I want to introduce my nickname. We're going to use this in our labs today, which is why I needed to get to this. It's called NK3. I call it the kitty edition, okay? And it's the kitty edition because the units are cute, okay? And from now on, we're going to use this version. So the total mass of my system, M1 plus M2, can just be computed by doing A cubed over P squared. Ironically, Laura, you were right the first time if you use the Kepler units, okay? So A will be measured in astronomical units. P will be measured in years. And the masses, wait for it, won't be measured in kilograms. They'll be measured in solar mass units. And that just makes things real easy, right? Like, if your stars have a separation of 5 AU, and if they have a period of 5 years, you can really quickly find the total mass of the system by doing 5 cubed over 5 squared, and that's 5 solar mass units. So it just makes all, remember how long it took to do an NK3 problem before? Now it's a little bit easier. Okay, here's one of the things. If you look at binary stars out in space, sometimes you can actually resolve the two as a pair, and you can show people the 2 stars, or you can observe the 2 stars. And there are some legendary examples of this, actually one of which I ironically showed you today. So I thought I wasn't going to need it anymore, but remember that when I showed you Alpha Centauri, of course, it's all right, technically it's a trinary system, but can we just pretend Proxima Centauri doesn't exist for a while? Because it just really gets in the way conceptually. So you guys can clearly see that I can resolve Alpha Centauri A and B as separate stars, right? Another cool example is the star Sirius. It's actually part of a binary with a weird object called a white dwarf, which I'm going to tell you about on our last day when I get to the black holes and stuff. Check this out. You can actually resolve Sirius and its white dwarf companion because they're close enough to Earth. Can you see how different their luminosities are? Sirius B is so dim compared to Sirius A that it's normally completely lost in the glare of the star unless you have a very sensitive instrument. But honestly, a lot of the times, the binaries are so close together on the sky, there are so few arc seconds that separate them, that you can't even resolve them with a telescope. An example of which would be one of my favorite stars to show people at the telescope, Albireo. Wait, am I sharing my screen or not?
No.
Let me do that. I'm trying to get to the point here, guys. Just bear with me. There's a star that's, what? There's a star that you can look at in the nighttime sky in the constellation of Cygnus, the swan. It's actually up in the sky right now. And when you look at this star with your naked eye, it looks like one star. But by the way, it's part of something called the summer triangle. I challenge you guys tonight to step out on your back deck, and if you're just having a sip of coffee or something, go ahead and see if you can find the summer triangle. 3 bright stars in 3 different constellations. Deneb is in the Northern Cross, or Cygnus the Swan, Altair and Vega. It's a gigantic 90-degree triangle. I was at a friend's porch 2 nights ago, and I stood out in her back deck, and the summer triangle is framed beautifully against the sky. So I know it's up right now. And part of Deneb is this little dirtbag star called Albireo. You can see it from your house tonight if you want to. And I love showing this to people through a telescope, because when you look at that one star, it resolves itself into a beautiful binary pair with a kind of creamy orange-yellow star and a brilliant blue star. A really nice demonstration of the differences between colors of stars. You might even be able to separate this if you had a pair of bird-watching binoculars. A small telescope will do it. What's interesting is this kind of encapsulates the joke about binaries so perfectly, because the yellow star that you see is itself another binary. It's an unresolved binary that's actually, this is not one star, but it's 2 stars. You just can't see them. So you can see, Laura, that trying to measure the separation between 2 stars to calculate their masses could be very difficult. And luckily, we have the Doppler shift to help us here. And I want to make this argument because it's part of our lab, which I'm going to have to really blast you guys through. But so be it. This is all part of our homework as well. Let's imagine this setup where we can use the Doppler shift or the Doppler effect to get first the velocities of the stars, and then I'm going to use the velocity to get A, which is the orbital radius, or whatever you want to call it. And of course, then I'm going to use the orbital radius to get the mass, okay? So let's remember our goal here. Our goals for a binary are get the A, get the P, and then find the mass. And this is important for you guys because our last homework problem and our lab is basically this job. Let's imagine that my star M1 is being orbited by star M2. And it's going around in a circle. The radius of the circle is A. That's the separation between the stars. Do you guys know the formula for the circumference of a circle from geometry? Anyone remember enough math for that? It's kind of a classic formula.
Pi r squared.
That's the area of the disk. Close, Evelyn. Remember, r squared is going to get you a length squared, right? But you're close.
2 pi r.
Yeah, the circumference of a star, but I don't want to say r, Evelyn, because I used a for my r, so the circumference of a circle is 2 pi, in this case, a. Imagine I watched star 2 go through one complete orbit. In one orbit, the time it takes is the period of the orbit. And if I do a little distance equals rate times time, I can say that 2 pi a, the circumference of my circle, that's how far it travels, is equal to the velocity times the period. I can rearrange this formula to get something that I call the binary star formula. Honestly, astronomers don't even have a name for this formula because they just think of it as common sense. But because I like to have names for my formulas, I call it the binary star formula. And it's a way of measuring the A by using the velocity. The orbit of my star, the orbital radius, is the velocity times the period over 2 pi. Now, why is that good for me? Because the Doppler shift lets me measure the velocity of any star I want. So that's how we get, and that's how we're going to do it today in lab. Now let's crank out our homework problem. And if I can't get through all the lab by 4, I'm just going to do a part of the lab with you guys, or I'll fast track it. I'll make sure I don't go. I know I've gone over time a bit here today, but I will stop at 4. Trust me on that. Why don't we at least do our final homework problem, because that's a nice test of how we put this all together. So Joel, do you have those problems written for us? Do you have the problems somewhere on your screen? Okay. Hey, hold on, class. Can I erase? Jose, are you still writing? Oh, can I erase here?
Well, did you have a question earlier?
Oh, did I miss something?
Oh, yeah, I was just, I mean, it might get off on a tangent. I was just curious, don't they like use binary stars to help discover black holes or something like that?
Yeah, so this is your first, you're learning in multiple stages. It's absolutely the same principle. The only difference with the merging black holes is that we're not viewing them using visual telescopes, but we're using something called gravitational waves. Now, one of my lectures in this course is supposed to be on special and general relativity, and it's a pretty wackadoo lecture. I've been wrestling with whether or not I have time for it. The problem with this class is as it goes on, the subjects just get cooler and weirder and more awesome. But then I start like running out of time, so I start getting kind of crazy, So next week is going to have to be a real blowout. We're going to have, I think the most important thing is to have fun, but it is sad because every single topic is so cool that I can't choose. It's hard to choose yes to black holes and no to supernovas. You know what I mean? It's like, it's such a pain in the butt.
Right.
So,
well, there is a solution. We could just do the office hours for class and talking about like material instead of doing homework.
Yeah, it turns out that
I'm just throwing it out there, like to get more information instead of.
It turns out though that
beat our heads against the wall.
Doing the problems. I don't know if you guys have noticed this, but obviously it's a long slog to get through one of these days, and having some different rhythms keeps it kind of more interesting. Like in the morning we kind of do the math stuff, then in the middle we do the talk stuff, and then at the end we do a little arts and crafts project. You know what I mean? And so those are just like different ways. And I kind of try to integrate them all so that we do talk about stuff. But I think the problems are actually a really important part of this course. And I know from talking to students who've taken it before that the doing of these problems tends to make you quite a bit better at math. And then when you go on to take your Algebra 1 and those other courses that you have to slog through, you're able to kind of decimate them and get through. So I think what we're doing is valuable here, not just because it's cool to learn about black holes, but you're learning some basic skills that will help in other courses and maybe even at life, who knows, you know? So, so I wouldn't trade those office hour problems for the world, Joel, is my point. And
No, I was just trying to be funny.
No, I mean, it's a thought that I've had before, trust me. This is still homework 7 now, right?
Yeah.
And it was chapter 15.
Yep.
50 something?
57.
57. Okay, why don't you read me the setup there? So this is a binary.
It's measuring stellar mass.
Okay.
The spectral lines of 2 stars in a particular eclipsing binary system shift back and forth with a period of 6 months. The line of both stars shift by equal amounts, and the amount of the Doppler shift indicates that each star has an orbital speed of 80,000 meters per second. What are the masses of the 2 stars? And assume that each of the 2 stars traces a circular orbit around their center of mass.
Okay. So just to kind of fast track this thing, the first thing that we're going to try to do is use the formula that I just taught you to find A, the orbital radius of the 2 stars. And we're going to do that with the binary star orbit formula, which is the velocity times the period over 2 pi. I'm going to suggest that we don't work in units of months because months have different numbers of days in them. The nice thing about 6 months is that's exactly equal to half a year. So our velocity is 80,000 meters per second. Oh, snap. Times 0.5 years, right? Over 2 times pi. But Laura, can you see that we have an issue with our units here?
Yep,
Usually...
we get seconds to years.
Yeah, let's fast track this by throwing our conversion right into the problem. That's a trick that pros do. Sometimes they'll do their unit conversions right inside the problem. I happen to remember that there's 3.15 times 10 to the 7 seconds per 1 year. So if I slap the pi times 10 to the 7 seconds up on the top, I should be good, all right? So do you guys want to try to punch that up? This times this times this, divide by 2, divide by pi. Should get a nice clean number out of that.
Two times 10 to the 11th.
What are my units?
Meters per second squared.
Careful. Let me do some unit balancing with you all.
Just meters.
Yeah, years with
Yeah.
years, and per seconds cancel with seconds on top, right?
Yeah.
It's just meters. Now listen, obviously our next goal is to plug this into the Newton's version of Kepler's third law. We could do the MKS version, but because I taught you the kiddie version today, let's quickly convert this into astronomical units. So it's 150 million kilometers. Do you guys know how many meters that would be? Oops, sorry. to go to AU? If it's 150 million kilometers, how many meters would that be?
Uh, 150 times 10 to the 9th.
Yeah. So why don't you guys tell me how many AUs I have for my A?
$1.3.
Oh, wow. Okay. I usually don't do this problem this way, so that's cool. Did anyone else get that? I just want to fact check.
Yeah.
All right.
Yep.
So watch how easy this becomes. Now we can find the total mass of the system just by doing 1.3 AUs cubed over 0.5 years squared. Nothing to it.
$8.8.
I'm sorry?
I got 8.8, but I could be wrong.
I got 9.5.
That is-
What? Can someone break the tie here?
I got 8.8.
Oh, wow, you guys are right. I did something wrong. All right. What are the units? You guys remember what the units?
Years.
No, this is a total
Years.
mass.
Kilogram?
8 kilograms for the mass
No.
of 2 kilos? That's like a block of cheese, you know?
That was stupid.
No,
What?
it's right in your notes.
Well, in the kitty edition, you said M total equals A cubed over P squared, and the A is
Oh.
AU, and the P is measured in years.
And what did I tell you the mass was measured in? Because that's a key point.
I must have missed that.
Solar mass units.
Solar.
Oh, yeah.
Sun equivalents. This is 8 times bigger than, more massive rather than the sun. Now, because they told us the stars have equal shifts in their Doppler shift, which you're about to see, that means each star, M1 equals M2, and each star is 4.4 solar mass units. All right? And that's the whole problem right there. All right. Does everyone have that? All right. I normally like to have an hour to do this lab, but because I'm not going to keep us here later than usual, for my sake as much as yours, but to not cheese out on our job, I'm going to try to do fast track on the lab, but also we'll just kind of do as much as we can and understand as much as we can in the half an hour we have left. Everyone okay with that plan? So if we don't get it all done, we'll just turn in whatever we can do. But I do believe that there is some value to this lab. The lab is called binary stars or spectroscopic eclipsing binaries. And let me share screen with y'all. We might want to get a good fraction of the printout here. Oh, I like those atlases. Hold on, I'm just trying to declutter my internet here. Wow, talked about so much cool stuff today. Lab. Oh, geez. Okay. This is our boy right here. There's some instructions that are kind of good to have, but honestly, we kind of need a few of these pages. It'd be nice to have this page and this page. Actually, all you're really going to turn into me is this page. So in the interest of time, if you want to just kind of watch me do it and keep the other pages up, what you really need is this page here, the very last one. I'm just going to hit print on the whole thing because I'm just gonna, it's going to be helpful. It says it's printing. Okay. I believe I found a more reliable way to connect my phone to the Zoom. I discovered a thing yesterday, so I'm gonna have to try to remember that again. Let's try going through this a little bit together to understand what's going on. So this lab attempts to kind of kick things up a notch. And while what you just learned about binary stars is true, it's hard for me to explain that you got the most basic overview of how we go about measuring the masses of stars. And just like with any project, there's all these little details that are hard to explain that you don't really realize until you're actually trying to collect some data and look at it. So let's go ahead and look at what actually happens when we study a binary star. The data that is in this lab is real, and it's based on a real binary star known as SS Boötes. Let me see if I can find the deets in here on SS. They call it SS Boo, okay? From spectroscopy data, we know that SS Boötes contains a cooler K-type star that's like a red giant, and then a hotter star that's a main sequence star. So what that means, class, if I can go to my share screen and kind of just use a digital whiteboard for a second, and I could actually make use of my drawing tools here. Let's imagine that we have two binary stars. We have a big red star, okay? And we have a smaller, cooler blue type star. Now, you guys will remember that red stars are colder and blue stars are hotter. But what's weird is when stars are red giants, they are colder, but they're really big. So we kind of have a hot star and we have a cold star. And one of the stars is orbiting around the other like so. We know this by studying spectroscopy, but this is an example where the two stars are so close together that we don't actually get to directly image the two stars. All we actually see is a single dot, a single point of light. But we know that there are two stars there because we see two sets of absorption lines shifting back and forth. Now, something you can do is you can plot something called a light curve for the two stars. And this tells you a little story, and I want to walk you through the story in your labs here. So follow along with me now on your lab screen, or watch my screen, I guess. And imagine what would happen if, keep in mind, class, that you're not seeing both stars. You're just seeing the unresolved binary. So all you see is just that thing, right? You're measuring the light from one single star. When the two stars are side by side, the light that you get from the two stars, the light that you get from the two stars is kind of at a maximum. And that's because the photospheres of both stars are contributing to the brightness of the dot that you see on the sky. But when one star starts to disappear and become eclipsed by the other, this is the point called first contact, where the little star is about to go behind the big star. As the star's photosphere starts to disappear, the brightness will take a sharp downturn. It will plateau when the little guy gets hidden behind the big guy. Now only the big guy's luminosity is contributing. And then when it peaks back out in position position E, it starts to peak back out, and you'll see the brightness rise again. This type of binary is called an eclipsing binary for obvious reasons. An SS Botez is an eclipsing binary, and this is the actual light curve data that some graduate student has taken. So I can see here the two stars are separated. I get the maximum amount of light from the two stars. And as the graph starts to dip, that's when one star goes behind the other, and there's the bottom trough. If I go too fast for you, if you have any questions, just kind of ask me. Otherwise, I'll assume that you understand what I'm talking about. So here's what we're going to do. We're going to try to analyze the relative luminosities of the two stars. I'm going to get into it with as little preamble as possible. So if I start going too fast for you guys, let me know, but I'm going to assume that you're following me. I am going to, how did I discover it last time? You start looking for the share screen, and then you activate this guy. This works. At least it worked yesterday. Oh, you know what? I'm probably not on Wi-Fi. Oh, I am. Uh-oh. Okay. Okay, we can do this here. One more time. Share screen. Well, that's stupid. I had this trouble with you guys last time, and then the class afterwards, I totally thought I had fixed it. Let me try it the other way. Let me try having the computer ask first and the phone ask second. Yes, makes no damn sense. Okay. Okay, so this is our light curve here for SS Botes. And what I'm going to do is I'm going to draw a sort of horizontal line at the trough of my star. Now, as you guys know, the actual brightnesses of stars are quite dim. Typical brightnesses for a star could be something like 10 to the minus 8 watts per meter squared. But no one wants to actually work in units of 5 times 10 to the minus 8 watts per meter squared because that's boring and it's not fun. So what we do is when we're measuring the brightness of a single star, when it's at a maximum, we're going to normalize it and just call the maximum 1.0, which is 100% of the greatest amount of light I get from the star. And we'll measure any dip in the light curve, any drop, as a percentage of the maximum. Basically, we're just using relative scaled units, 0 to 100, right? 100%. Furthermore, because of the inverse square law, if you think about it, normally, as I chastised Will for at the beginning of class, brightness and luminosity are not the same thing. This is how much light you get, and that's how much light you give. But Will, the exception is binary stars, because for binary stars, we know they're at the same distance. So distance is not what's changing their luminosities. That means any change in brightness is a change in the luminosities of the stars. Very clever trick. Okay, when we're at 100%, let's call one star the hot star, and let's call one star the cold or the cooler star. When the two stars, let's look at the cartoon real quick. When the two stars are side by each, right? Both stars contribute to the luminosity of the star in the sky. So in other words, the luminosity of the little hot star plus the luminosity of the big cold star is equal to 1.0. But when the hot star goes behind the cooler star, when I have my primary eclipse, down here at the trough, only the colder star contributes to my luminosity, LC. And I can use this to measure the relative luminosities of the two stars. So you guys saw that I just made a vertical line. Do you guys know how to figure out what this is here? What would this value be? If that's 0.5 and that's 0.6, what's this doodad?
0.58.
Very good. So let's go to our data sheet. That tells me that the luminosity of the cold star is 0.58. Now, if you're wondering about the units, there are no units because this is kind of arbitrary luminosities. We're just trying to figure out, is the hot star more luminous or is the cold star more luminous? So what would LH be in that case?
0.42.
Exactly, because if you subtract 1 minus 0.58, you get, right, very good. So that already gets us 2 of our answers right there. So 0.58.
Well, that doesn't make sense, though.
Oh, does it or doesn't it? Tell me why. I want to hear it. Walk me through it. I know what you're thinking,
Well,
but
so like the hotter star, like what
yes,
you would expect it to be brighter because it has more energy.
beautiful.
But,
you know what? But here we have the hotter star being dimmer, or being
like,
less luminous.
so like if you compared like the moon and the sun, like speaking of like ecliptical stuff, the sun would be the LC and the moon would be the LH, or is that backwards thinking?
Joel, you are very perceptive. In fact, Joel, you're so perceptive that I didn't expect anyone to notice this or care. So I was actually going to hide this detail from you because
I'm a numbers guy.
All right. So let me let me explain.
I might get lost with words, but numbers don't usually fool me.
It turns out that Joel, here's the difference. You would be, if all stars were the same size, then you would exactly be right. The hotter star should be the brighter one. But remember, Joel, if you can, hold on, sorry, I'm trying to do several things at once here. I can explain this really easily to you, okay? If you have a star, okay? Oops.
Uh-oh.
Here we go. Wait, hold on. And your star has a radius r, right? Then the temperature is controlling how much light comes off of a 1 square meter panel. And the formula that you were referring to there is the so-called Stefan-Boltzmann law. The brightness of a star is sigma times t to the 4th, which is the brightness on a single square panel. But what you forget about, Joel, is that stars of different radii have greater or fewer square panels on their surface, more tiles to radiate. And as you remember from the inverse square law, if you calculate the brightness that way, it's the luminosity of a star, its total light over 4 pi r squared, where r is the radius. What happens if you set those two things equal to each other? You then discover that the luminosity of a star, its total light output, is 4 pi r squared times sigma t to the 4th. This is a classic rule of astronomy. I was actually supposed to include this in today's lecture, and I thought I could skip it, and now I'm realizing that this is why I couldn't. So what this means is the luminosity of a star not only depends upon its temperature, Joel, but its radius. And if the radius of one star gets too big, it can overcompensate. For instance, I had a wicked cute slide for this in today's slideshow. This is, by the way, I'm gonna start our class next time with this law. This is what is known as the Stefan-Boltzmann law for stars. And if you don't like the math side of it, here it is in a cutesy nutshell. Here I have two stars. This is the case that you were talking about. One star is at 6,000 Kelvin, one star is at 10,000 Kelvin. This star will pump out more luminosity because it's hotter. That's what you were talking about. But now imagine I have two stars, both at 6,000 Kelvin. If one is a red giant and way fatter, even though they're the same temperature, this star will be more luminous because there's more surface area to shine away. The implication for our problem, Joel, is yes, this star is the hotter star, but you will remember in the description that they told us that this is a K-type subgiant star. Oh, sorry. What are you guys seeing right now? Oh, yeah, okay, look. The colder star is actually a red giant, but the G-type star is a dwarf star. So, Joel, the reason why that's okay, it must mean that the cooler star is so much fatter than the hotter star that it's pumping out more light. But very good observation.
Okay.
All right. Next piece of business. I can use this information to get the relative radii of the stars. And hear me out on this, guys. Let's imagine the moment where my first star is just about to dip behind and be eclipsed. I can measure the time of first contact. I'm going to call that T1, right? And I can measure the time of last contact when the star goes behind. And what's cool about that is from T1 to T2, I know that the star will have traveled one hot star diameter to go from there to there. If I know the velocity, I can use distance equals rate times time to calculate the velocity. Meanwhile, I can also get the time from first contact to the time of whatever they call it, last contact. And during the time from just before the eclipse starts to just before it ends, during that time, the hot star will travel one big fat cold star diameter. So I'm basically using the fact that it takes time to cross the star as a measure of the relative radii of the stars. I don't know if that made sense to you guys. It makes sense to me, right? But like, it's like a car, right? Like if you have a van, if you
Oh
measure,
God, these math travel things. The
yeah,
car's traveling at X speed and the
but
oh
it's just
God.
distance equals rate times time, right? If my van is traveling 1 meter per sec, I think you understand. Look, let's just get to the business of it. To measure the times of first, where's the primary eclipse here? So first contact is going to be right at position B, where the star is about to go behind the star, and that's when the light starts to dip. And second contact is when it gets completely eclipsed. So we can see that happening here on the real data for SS Botes. And what I'm going to do to measure the first and second contact, actually, for this one, I might want to use the tape. Hold on. I'm going to take my ruler and carefully, very carefully, I'm going to get the point of first contact. Now, there's a bit of an art here, because if you look at the data points, you can see there's a bit of noise, and it's kind of difficult to determine where the light curve is actually starting to dip. I'm going to go ahead and be bold and say, well, what do you guys think? Do we want to say the dip starts there, or do we want to say the dip starts there, or what do you think?
The second one.
Like that guy right there?
Yeah.
All right, cool. So let me get my finger on that. It's hard. It's easy to drift by a box here. All right. Let's get my second contact. I'm going to say it's... it's a little noisy over here, but I guess I'll say it's this one here. There's my T2, okay? That's T2. This is my T1. And then my third contact here, oh geez, I guess I'll start it here. Okay, now the scale of this is kind of weird. First of all, do you guys notice that they're using the Julian calendar to measure days? One of the weird things about astronomers is they don't use the Gregorian calendar because the Gregorian calendar has wacky leap years. By using Julian calendar days, you don't end up, you kind of have the same number of days per year of 365.25. It's just a weird quirk of astronomy, but these are basically days. Now, once you guys look at the interval there, do you see how the interval is 331.8 to 332.0? There's 20 boxes in between those two. Sorry. So if my time interval is 0.2 days, because it's 0.2 days in between these big marks here, and if I divide 0.2 days by 20 boxes, that's 0.01 days per box, okay? So let's see if the six of us or whatever we got here, let's see if we can figure this out. If this is 331.8 here, it looks like I'm 1, 2, 3 tick marks back. Can you guys tell me what that would be if it's 0.01 days per box?
331.5.
Oh, no way. Dude.
Oh.
Look,
Oh. So you're minus.
It's not 0.1 days per box, right? It's 0.01 days per box.
So would it be 0.77?
Yeah, exactly. So this is, think of this as 331.80. 331.80, 331.79, 331.78, 331.77. Let's get that down for our first contact. Our first contact is 331.7 days, right? Okay, with that in mind, now we can go a little faster. Let me go sideways again for my own sanity. What would that guy be, T2? That second line. Just for reference, in case this is getting a little confusing here. Hold on, I'm just trying to. That is 332.00. So this would be
331.94.
99,
Yeah.
98, 97, 96, 95. Good. I agree with that. I'm going a little quick here, so please forgive me if some of you guys are getting a little confused. I'm trying to be quick and clear at the same time. Those two things don't go together. How about this third tick? Or this third contact point? That's 332.19, 18, 17, 16, right?
Yep.
So 332.16. Okay, now I will use distance equals rate times time to come up with what I call the scale radii. These numbers aren't going to mean anything in themselves, but the relative difference or the ratio of these will tell you how much bigger the cold star is than the hot star. So I believe the formula that we want is pi times the change in times divided by the period. And you'll notice here that they've given the period for us in days as 7.60614 days. I'll probably just round the period to be like, because we don't need the 10th decimal place here, right? We'll just do 7.606 days. Just keep it. That's even a lot of sig figs, if you ask me. Oh, I guess there's 1, 2, 3, 4, 5. Yeah, you know what? Who cares? So our cold star radius is pi times T3 minus T1 over the period. So let's do pi. I'm going to go vertical here. Excuse my screen. Pi times open parentheses. Now we got to go to T3. 332.16 minus T1, 331.77. I'm going to close my parentheses, and then I'll divide it by this period. Did I hit divided by? Oh, shit. Okay, I blew it. Times 332.16 minus 331.77. divided by 7.606. And because I'm lazy, I'm just going to round that to 0.16 here, okay? So if the cold star radius is 16%, then the hot star radius, is pi times T2 minus T1 over the period. So I'll do pi times open parentheses 331.94 minus 331. I should just keep this over here. 331.77 close parentheses divide by 7.606, and I get 0.07. So what does this tell me? Not much, except the hot star is approximately twice as big. Sorry, let me try that again. The colder star, the red giant star, is twice as big as the hot star. That's why they call it a subgiant, because it's not like Betelgeuse sized. It's just a little bit bigger. Okay.
Now that's the percentage of the mass of the sun.
No, these are radii. What this is
Okay.
This is a percentage of the semi-major axis of orbit. So what they did is they assumed that the entire trip around the orbit would be 2 pi times the semi-major axis. So this means that the cold star, its radius is 16% of the orbital radius.
Oh, okay.
7%.
Okay.
Okay, look, there was quite a bit more to do here where we were actually going to start to use the spectroscopic data. But it would take it wouldn't take that long to do, but I realize now that it'll at least take another half an hour to do. So here's what we're going to do in the interest of sanity and fatigue and all the rest of that, okay? I'm going to stay true to my promise because I made that promise. We're going to stop at 4, okay? And you guys are going to turn in just the eclipsing part of today's lab. And there's still plenty for us to learn next time. We're going to do a lot more on binary stars, so it'll be okay that we didn't do the rest of that, okay? Everyone on the page there? Okay, all right. But we did part of today's lab. We did half of it. You will turn that into me, okay? I guess that's it until next Tuesday, right?
Okie doke.
Next week will be our last 2 lectures. So we're gonna have to make them fun, okay?
Black holes, black holes.
Yeah, I'm gonna get them in there, I promise you. I think I can do this.
Awesome.
All right, I'll make sure to post this recording, and if not, I'll see you guys on no other thing. Everyone, oh, Joel, I'll grade your homework. I mean, your test, okay? I'll do it right now when I hang up. Okay, I promise. All right, bye guys. See you later.